of RNA, the mosquitoes were also taking them in, and somehow, even though the virus Zika was still in the gut of the mosquito, it was no longer in the saliva. These mosquitoes were becoming refractory to transmitting the virus, a little bit the way Wolbachia does it. But instead, this is pieces of the genome of the replicons themselves. So, thank you, Célébrons, for always introducing me to the right thing to do. See, that's why these global exchanges work both ways. And now in A-Star, I'm revisiting what I started about 30 years ago as a PhD student when everybody laughed at us, RNA vaccination. So at the time, in 1994, the first messenger RNA was put in a mouse, and 3 years later we said, well, replicons self-amplify RNAs. They're basically like picornaviruses, alphaviruses, flaviviruses. You take out the structure proteins, you still have all the replication you need. That's a messenger RNA that you can give. And if you stick in an antigen in that place, like influenza nucleoprotein, then you're going to have a messenger RNA that makes 1 million copies, makes a lot of danger signals and antigen, and we show that this was as good a response as DNA vaccination, which was actually what all those people were trying to do in the 90s. We now repaint the picture and make it look like messenger RNA was always the goal. It was never the goal. It was destined to fail. And luckily, even though it was in so many clinical trials, it's thanks to COVID that it got into enough people to show that it's kind of efficient. But really, it's not that efficient because it requires boosting the immunity brains. And the future is probably like somewhere along the lines of a self-amplifying RNA vaccine that's made safer. And this is one of our goals. It's the goals of BioNTech and Moderna, but they're not willing to do the R&D for it. So we know that the ideas are there. And this, I think, is also where we at A-Star, who have a huge campus that's working on manufacturing of RNA and works on all the other sides of RNA, could really couple with places such as here that is doing vaccines and focused on other aspects of it. And I think this is the future that we could all share. And maybe the third time that Senegal can affect my life. So with that, I really thank you all. And to the young people, my message of young baby to you, find your niche, wedge yourself into that niche like a crab, right? Because there's big rocks everywhere. Everyone is one little shell in a rock, and you get in there and don't let go. Half the things you discover will be wrong. That's okay. Let it go. Especially after my first Nature paper, the backlash against that was just as violent, and it's hard to deal with until you realize, okay, at least half of it was okay. You are not your science, so get a life outside of the lab and enjoy it. That's really important to surviving in this game. You will hear you are wrong with almost all of your career, but they're actually wrong too. So just keep that in mind. And science is hard work, good luck, and perseverance. I've realized that really half of it was that everybody else around me just decided to get a real job, and they gave up. And really, we're the only idiots that are still doing this after all this time. And certainly, especially for your children, the ones that those of you have children that are super weird, like the way they talk about anything, and never say that, stop it, that's not real, that's unrealistic. Let that go. Because that's what my parents let me do all my life. And for that, let your imagination run wild, and I mean wild. And then learn to reel it in. Thank you.
Thank you, Marco, for sharing your good work at the A-Star ID Labs, for reminding us how impactful and influential the Institut Pasteur de Dakar has always been to its collaborators, and reminding us of the positives of finding your niche, adapting to different environments, and dreaming creatively, innovatively, and big. Please help me give another round of applause to Professor Marco. Speaking of doing a great job, it is now my honor to introduce someone who has been excelling in vaccine and immunity research in Africa. Professor Ed Clark. Professor Ed Clark leads the vaccine and immunity research team at the MRC unit in the Gambia for the past 12 years. He is a professor of pediatric infection, immunity and global health at the London School of Hygiene and Tropical Medicine, and he continues to practice clinically as a consultant pediatrician in both the Gambia and UK. Additionally, he is a member of the Gambia National Immunization Technical Advisory Group. At the MRC, Professor Clark and his team have recently accomplished several vaccine trials, including phase 1 to 3 trials, resulting in licensure of the first pentavalent meningococcal ACYWX vaccine, the novel poliovirus vaccine type 2, and expanding the program of immunological and epidemiological research related to Group A streptococcus. Professor Clark is currently co-leading an ambitious CEPI-funded network to expand clinical vaccine trial capacity across West Africa, aiming to deliver Lassa fever and other trials related to delivering CEPI's 100-day mission. Without further ado, please help me welcome Professor Ed Clark.
Okay. That's me running. Okay, so thank you very much. So it's a real huge honour to be invited to speak here at this prestigious event. And similarly, I didn't expect that to be read out. That's almost given the entire talk away, but there we go. So I'm going to talk. So I'm Ed. I'm based at the MRC unit in the Gambia. I'm going to talk sort of broadly about innovations for vaccine equity in its sort of broadest sense. And warm wishes I came across on the boat. I'm probably the only person who came from another country via sea, maybe, so I came across the ferry yesterday. So warm wishes from the Gambia to all our Senegalese colleagues. You can see this is also a very large team. So, as I'm sure most of you are aware, the WHO Immunisation Agenda 2030 is described as a global strategy to leave no one behind. So it's really got vaccine equity right at its heart. And it's really a vaccine policy and research agenda for the coming decade. And this is highly relevant to, us working in the Gambia, you working in Senegal and elsewhere in West Africa. And of course, this is also highly relevant thinking about, this is just DTP coverage. You can see in dark green there, nearly a third of all under-immunized children globally live in West and Central Africa. And then if you add the yellow sector, half of all under-immunized children live in sub-Saharan Africa. So clearly this is a significant issue in this part of the world. But obviously, as everybody in this audience, I'm sure will be clear, vaccine equity is not just about children in the Gambia, children in Senegal, children in West Africa getting the vaccines that children in high-income countries need, although that's obviously important, but also about thinking about the development of vaccines for pathogens where the burden of diseases in this part of the world, or predominantly in this part of the world. So tuberculosis, we've got a big program of research related to TB immunology, group A strep, which I'll touch on in a moment, Lassa fever, other viral hemorrhagic fevers, many of the things that you're doing here. And this really requires an understanding of naturally acquired immunity to these pathogens in order to look at correlates of protection, transmission and disease burden. And lastly, thinking about vaccine equity and very much thinking about what you're doing here and what we hope to be doing with you a little bit in the future. Obviously, regional vaccine manufacturing is also vital, and regional clinical trial capacity. And Dr. Sal may think I've been camping in the IPD garden recently as I've been visiting so often with the hoping to forward clinical trials with the Institute in the future. So the Immunisation Agenda 2030 has got a bunch of different impact goals and 7 indicators, and at the MRC unit we're doing trials really across lots of different areas. So pneumococcal research, looking at different vaccine schedules and RSV vaccines. Polio I'll touch on, and that really is the other end of the spectrum for the novel polio vaccine that we've just heard about, actually. Yellow fever, some of the work we're doing with CEPI, meningococcal vaccines, again, I'll touch on very briefly. Quite a program of work related to HPV and STIs and alternative schedules, as well as finally sort of maternal vaccination. So just a couple of very quick examples. So we've recently, which was already mentioned, so we've recently completed the first trial of a pentavalent meningococcal conjugate vaccine, so ACYWX vaccine, really aiming to combat epidemic meningitis across the meningitis belt, which, as you know, stretches from here in Senegal and Gambia over to Ethiopia in East Africa. So based on this trial, the vaccine was pre-qualified in July last year, got a SAGE recommendation, and then was introduced in Nigeria as the first pentavalent vaccine, really aiming to combat epidemic meningitis in this part of the world. And the expectation is that this vaccine will replace Menafrivac in due course, really for meningococcal disease control in the meningitis belt when supplies become available. And then just really thinking very much at the other end of the spectrum, but the issues with emergence of vaccine-derived polio, which has really set the polio eradication initiative back. So we've recently also completed the first phase 3 trial of the novel poliovirus type 2, which is designed to have fewer genetic mutations, so fewer reversion events. And again, with the data that was generated as part of the emergency use listing when it was widely used across West Africa, of course, including in Senegal and the Gambia, this again got pre-qualification and has really been influential, and hopefully will really drive the end of the polio globally. But now moving on to think, so that's just a couple of brief examples, but of course, as we all know, having vaccines is one thing, getting them to the children that need them is an entirely different thing. So just to sort of present a brief bit of data and a bit of research that we've been doing in this field. So rather than polio, of course, we've had polio vaccines that really, in theory, could have eradicated polio a long time ago, but looking at instead measles. And again, if you look at measles containing vaccine coverage globally, you can see, and this is first dose, let alone second dose. So the WHO, in order to control measles, recommends a 2-dose measles containing vaccine coverage of 95%. And you can see really globally, even at 1-dose coverage is way below 95% in most countries, and certainly 2-dose really across the world. And if you look in West Africa, Senegal's doing pretty well, a little bit better than the Gambia, actually. It's quite close, but this is still 1-dose coverage, quite close to 95%, but a huge burden of under-vaccinated children in Nigeria, for example. And even in a small country like the Gambia, there's significant variation in vaccine coverage, so that even if you've got overall reasonable coverage, you've still got pockets of the population who are under-vaccinated where you can have outbreaks. And microarray patch-based measles-containing vaccine technology offers a potential, has been considered to offer a potential to sort of close this immunity gap, really, to make it easier to get these vaccines to the children that need them, because we've obviously got an extremely effective vaccine in principle. So microarray patches, so the trial that I'm going to talk a little bit more about shortly. So this is the microarray patch. So it's just the same measles and rubella vaccine. So it's the live attenuated vaccine, and it's embedded within these microneedles, essentially on the back of a sticking plaster. I'll show you some more pictures in a moment. The patch is placed on the skin. The needles penetrate and just dissolve, delivering the vaccine. So there are a number of kind of key potential advantages, and I hesitate to say these are potential in the sense that this is still very early phase trial data, but they're very easy to administer. So they should be easy to administer with minimal training. Anybody who's been aware of polio campaigns, of course, anybody can pretty much give polio drops. Red Cross volunteers, students, anybody can give polio drops effectively. But that's, of course, not the case if you want to do a large campaign with a measles and rubella vaccine where they're given subcutaneously. So the ease of administration could be critical. They're also thermostable, or expected to be more thermostable than the standard vaccine, so again, decreasing cold chain requirements. They're pain-free, which is, of course, an advantage to all of us. They're single dose preparations, and if again, this really gives the opportunity to make sure every opportunity to give a measles and rubella vaccine is taken. So if you've got a multi-dose vial with 20 doses, and you just one child comes to your clinic, the person may be unwilling to open that vial for the one child. So the single dose preparation is potentially an important advantage from that perspective, really, in making sure every opportunity is taken. Reduced costs potentially overall if you include all the costs, no sharps injuries and no sharps waste. And that's a picture of one of our clinics. Well, not one of our clinics, well, a picture of a clinic in the Gambia where really incineration is a major problem. So these have been termed by the Vaccine Innovation Prioritisation Strategy, which is a group including Gavi, UNICEF, the WHO, Bill and Melinda Gates and PATH as the highest priority transformational innovation for overcoming immunisation barriers in low and middle income countries. So we've just completed the first trial of these using maps to administer these vaccines to children. So this is a map produced by Micron, who's a spin-out from Georgia Tech originally. So this was an AIDS de-escalation trial, so it was the first trial of microneedle patches in children at all, and it was the first trial of these measles and rubella patches. So we recruited 45 adults, followed by 120 measles and rubella vaccine primed toddlers, and then 120 measles and rubella vaccine naive infants at 9 months, which is the standard schedule in the Gambia. So some of them usually in pediatric trials, at least this was a double dummy design. So essentially all participants in the trial either got a measles and rubella micro needle patch and a placebo subcutaneous injection, or they got a placebo micro A patch and a subcutaneous measles and rubella injection. So this was really to ensure double blinding as possible. Obviously, if you've got two different routes of administration, you can't double blind without using a sort of double dummy approach. So this was really to make sure we got as robust a safety data as we could. This is the patch in close-up, so it's just essentially it's the Serum Institute of India's measles and rubella vaccine. In this case, it's the same dose. So this trial wasn't exploring dose sparing specifically, although could do in principle in the future. And it's a little neat little device. It's a young man who's been in lots of media outlets at various points, wearing his patch there, sitting happily. In this case, it was a 5-minute application time, and again, that's something we're exploring going forward, but clearly not too bothered by having his measles and rubella injection. So just to go through a few data from this trial, so this is just infant data, so randomised and vaccinated 120 infants, they're all in the safety population and 118 in the immunogenicity population. Nothing really to say about demographics, slightly more females than males, but reasonably well balanced between the two groups. Somewhat different tribal groupings, but again, nothing that we would expect to impact on safety or immunogenicity. I'm coming on to the safety data. So we were particularly interested, of course, in local reactions. This is giving a live attenuated vaccine essentially into the epidermis or dermis. So local reactions are obviously a key initial safety concern. And essentially, you can see we saw no tenderness essentially with either the micro needle patch, the active patch on the top left, and the placebo patch top right, and then the subcutaneous injection. So really nothing to see in terms of tenderness. A little bit of erythema, a little bit of redness associated with the patch application site, perhaps not as much as we expected, and not really particularly associated with the active virus, interestingly. So we really saw that with the measles and rubella vaccine patch and the placebo patch. And that's a local reaction. So this is just a grade 1 reaction, so not of any safety concern in itself, a very mild, a little dot there, as you might expect. Then in terms of induration, so we saw quite a lot of induration. This is clearly associated with viral replication, so you can see you get a peak of induration at around day 9 or 10. That is associated with the active patch that you don't see with the placebo patch. Interestingly, we saw, as perhaps you might have predicted in the toddlers who'd already been primed with the measles and rubella vaccine, they got a much earlier induration, so they were obviously getting an earlier immune response, driving this local swelling at the vaccination site. But again, these were all mild. Then think about the unsolicited safety data, so all the other events. So we saw quite a significant amount of hyperpigmentation in dark skin. Essentially, I can show you a picture. So following vaccination, you get the local inflammation, and we saw quite a lot of hyperpigmentation with the MR patch. a little bit of other mild reactions associated with the patch, and then really everything else was mild to moderate. So upper respiratory tract infections, all the other things that you see in children in the Gambia, almost all mild and moderate. So really nothing to suggest this patch was causing any other concerns. And then coming on to the immunogenicity, so safety all looked very reassuring, really nothing in the way of significant local safety events and nothing else to be of concern. And then the immunogenicity, so this is using serum neutralizing antibody assays, so the standard measure, the standard correlative protect associated with standard correlative protection, so this is a CDC assay. So baseline, essentially, there was very little measles seropositivity in the population, reassuringly, so very little measles circulating. And then whether the measles and rubella vaccine was given by patch or by the normal subcutaneous injection in red and blue respectively, you can see you got a robust immune response, essentially comparable immune response, whether the vaccine was being given by patch or by needle and syringe, and this was maintained to day 180. Similarly with rubella, very little circulating at baseline, and as you would expect with a single dose of rubella, very robust immune responses, so everybody seroconverted from baseline, so everybody was seropositive at day 42, and that was maintained to day 180. So again, both good, strong safety data, but also good immunogenicity data. For those interested, the titer distribution, the antibody titers were essentially identical, whether the vaccine was given by patch or by subcutaneous injection. You can see post-vaccination, they're essentially the same titer distributions for both measles and rubella. So this generated lots of interest on the Gavi website and the BBC in terms of demonstrating at least proof of principle for measles and for microneedle patches in children, looking at both safety and immunogenicity. So we're going forward now, looking at a phase 2 trial of these vaccines. This is still early phase development, looking at a reduced wear time. 5 minutes is a long time to keep a patch on realistically in a small child, and also reduced dose of the viruses. There are various other alternative map designs, so including not dissolving but solid needle maps. So again, expecting to start another trial of those next year. Phase 3 trial designs, there's lots of interesting questions about how this will move from the current proof of principle to sort of phase 3 trials, and we've recently published an article with the WHO and lots of other people looking at issues related to the phase 3 trial design. Manufacturing scale-up, we don't have significant expertise in that, but that's clearly an issue that many people will understand. Clearly manufacturing a patch is quite different from manufacturing and filling a vial, and lots of other potential antigens. So we're hoping to explore hepatitis B for birth dose vaccination, for example, which could be much easier really to get timely birth dose coverage with hepatitis B, for example. So that's essentially work in progress. So watch this space, but hopefully this will move forward. Hopefully this will move forward significantly over the next year or two. And lastly, I just wanted to touch on some of the sort of more discovery type research that we're doing in the Gambia, again related to vaccines, thinking about sort of transmission and immunity cohorts, because you can get a lot of information from studying transmission of infections at a household level, for example, between individuals, between different age groups, within compounds in this setting in the Gambia and Senegal, and within villages, within districts, and obviously at a wider scale than that. And this is obviously infectious agent specific in terms of what level of detail you're looking at. It's a powerful tool for understanding disease transmission, of course, within households or within larger areas for looking at correlates of protection, genetic diversity, and disease burden. So we're doing quite a lot of research on this related to TB to understand correlates of protection from TB, so who gets infection and who doesn't if they've been exposed to tuberculosis, for example, group A streptococcus, which I'll come on to in a moment, to just provide a few bits of information on that, respiratory viruses, and increasingly work on HPV transmission within households and within polygamous marriages, for example, to understand how these viruses are being transmitted. So group A streptococcus, I hate to mention a bacteria in this setting, but hopefully I'm allowed to. So really, really key pathogen in this part of the world, I think perhaps under-recognised. I guess even in an audience like this, perhaps it doesn't get a lot of attention. So group A streptococcus is predominantly in high-income countries a problem of invasive disease, causing streptococcal toxic shock syndrome, which is clearly increasing and clearly causing a problem. But in this part of the world, as anyone who's practiced clinically in this part of the world in either paediatrics or in early adults, the real burden is post-streptococcal rheumatic heart disease. And in the absence of cardiothoracic surgeons, this is really leading to end-stage cardiac failure really in late childhood or early adolescence, with a huge burden that we see certainly in the Gambia and I'm sure in Senegal in the same way. So a real need for a group A streptococcal vaccine. Rheumatic heart disease is historically considered to be triggered by throat infections predominantly, but increasing evidence suggests this is probably also triggered by skin infections, which again are very common in this part of the world, as well as potentially asymptomatic colonization. So we've been doing quite a lot of studies looking at this, really trying to understand dynamics within households and spread within individuals. So collecting, for example, in this study, over the course of a year, collecting monthly swabs looking for both carriage and disease, additional swabs associated with pharyngitis or skin infections, as well as detailed swabbing after particular infectious disease, after particular carriage events, really to understand the duration of carriage. And lastly, subgroups really where they were swabbed every week, both in the throat and the skin, really to understand how rapidly these infections are spreading within households and how quickly they're cleared from individuals. Also collecting data on systemic immune responses, so looking at serum and dried blood spots to look at immune generation, as well as mucosal samples to look at mucosal immunity within following strep A colonization or disease. So just a few headlines. There's a huge genetic diversity. Historically, M protein has been considered to be a key target for group A strep vaccines, but really there's a huge genetic diversity, not only within communities, but also within households. So it's really very much less likely, and M protein is very much less likely to make a suitable target for future group A strep vaccines. We saw rapid antibody responses there over the first years of life, both to conserved carbohydrates as well as conserved proteins within the vaccine. And even looking at mother-infant pairs, you see the antibody responses in the infant waning rapidly, and you can see or you may be able to see in the blue dots associated colonization events increasing the antibody titers even in these early infants associated with early colonization and early disease endpoints. So we're going on to establish a controlled human infection model for group A streptococcus over the coming years. So this is really trying to understand whether these observational studies that we've generated, looking at both functional binding and additional immunological markers, really whether we can associate any of these serological markers with protection from strep A pharyngitis, essentially. So this should generate interesting data moving forward with lots of collaborators. And lastly, I think, hopefully this will play, and it's nice to see Heidi in the audience. So essentially, clearly, again, having vaccines does not mean people are going to want to take them. So we've also got quite a program of qualitative research looking at looking to understand barriers to vaccination in individuals. And this is just a little video that we've made. It's probably the only place we can play this where at least a significant proportion of the audience will understand the language. So hopefully this will clarify. Is that a sound? Good. So there we go. So hopefully, even if you don't speak Wolof, lots of people I guess do. So even if you don't speak Wolof or Mandinka, I guess you got the message there. So anyway, that's a little video that we've generated, which hopefully will positive message around vaccination in this setting. So that's it really. So thanks. Just mentioned to lots of different funders who funded lots of different parts of this work, and to all our colleagues and friends in the vaccines and immunity team and around and in Senegal. Thank you for listening. Thank you.
Thank you, Professor Ed, for sharing your innovations in vaccine delivery in low and middle income countries through microarray patches, infant induration, immunogenicity, strep A diversity, and for sharing the learnings you and your team have discovered along the way. Moreover, we are reminded by your key message that vaccines do save lives. We wish you the best in your phase 2 trials and the design of phase 3, which undoubtedly will benefit all of us. I'm about to dismiss us for a brief break, which will last just 30 minutes, and we will restart here at 10:50 a.m. Following this, we would start our first panel discussion of the day. Before we go out, please kindly help me to give another round of applause to both our speakers for the knowledge that they shared and for taking time out of their busy schedules today to be with us. Thank you. the Foundation for Innovative New Diagnostics, and the Institut de Recherche et de Développement, France. Diatropics focuses on development and manufacturing of rapid diagnostic tests for neglected and epidemic diseases in Africa. Dr. Shahtijan, could you please come to the stage? Next, we have Dr. Marie-Angélique Sen. Dr. Marie-Angélique Sen is the head of Advanced Vaccine Bioprocessing at the Institut Pasteur de Dakar, leading the establishment of a new laboratory responsible for the acquisition and transfer of novel technology. Marie-Angélique began her studies in engineering school, studying material science, mechanical engineering, quantum physics, and relativity, while conducting research at one of the French Atomic Energy Commission laboratories. Afterwards, she joined the graduate program in Seoul National University, Korea, to specialize in micro-nano-engineering while overseeing the inter-university semiconductor research center's photolithography equipment, quality control, and offering consulting services for local Korean companies wishing to integrate micro-nanotechnology to their point-of-care devices. She's worked on projects from various fields such as agriculture, green energies, semiconductors, optics, and health, amongst many others. Dr. Sen now specializes in vaccine manufacturing and to apply her previously acquired knowledges to this field to contribute in the effort to advance equitable access to vaccines. During her PhD at McGill University in the Kamen Lab, she obtained a patent as main inventor in collaboration with Sanofi Pasteur, focusing on the genetic engineering of the viral cell vaccine production platform, providing new possibilities to quickly generate high-throughput, globally accessible, and pandemic-ready cell-based vaccine platforms to efficiently protect global populations from current and emerging diseases. Please help me welcome Dr. Marie-Angélique Sen. I would now like to introduce Dr. Yahya J, who is the head of the microbiology department at the Institut Pasteur de Dakar. Dr. Yahya J at the IPD is an associate professor at the Sheikh Anta Diop University in Dakar. He is a distinguished bacteriologist and molecular geneticist. Dr. J brings extensive expertise in genetic engineering, bacterial pathogenesis, and the development of bacteria-based delivery systems for biologics. His work is at the forefront of addressing antimicrobial resistance in sub-Saharan Africa, where Dr. J leads a comprehensive portfolio of research and initiatives targeting this critical global health challenge. Please help me welcome Dr. Yahya J. I would also like to finally introduce Dr. Lati Gay, who might join us a bit later if he's not here already. Dr. Lati Gay is a postdoctoral research fellow at the Institut Pasteur de Dakar. He obtained a PhD in molecular cell biology of infectious diseases from the West African Center for Cell Biology of Infectious Pathogens. His PhD work focused on the mechanisms of erythrocyte invasion by Plasmodium falciparum, with a particular focus on malaria parasite biology and blood stage vaccines. Dr. Lati's goal is to contribute to developing comprehensive biological tools to help address the challenges associated with malaria vaccine development. His short-term career goal is to assess the effect of Plasmodium falciparum genetic diversity on vaccine efficacy. In the longer term, this will contribute to developing strategies to enable the design of next-generation malaria vaccines that can circumvent the challenge posed by strain-specific immunity. Dr. Latige is also has received several awards, most notably the ARIF, which is the African Research Excellence Fellowship, as well as the Arise Award. And he's a prominent and promising researcher in the field of malaria vaccine development, working together with universities such as Yale and Oxford. I would now leave Dr. Xavier Berthet to moderate the... Oh, Dr. Latigay is here, please. Give him a round of applause. I'm sorry, I didn't see you. Welcome, Dr. Gay. Okay, so we will now start our panel discussion, and Dr. Xavier Berthet will lead this. Thank you.
Thank you very much, Aisha, for this very compelling introduction. Today, it's a session from the Pasteurians to the rest of the world, and these ladies and gentlemen have a secret that they would like to share with you. They all are brilliant Senegalese that went to study outside and that we were able to capture back to the IPD. So they are what we call repats from Indonesia, from Canada, from France, from the Gambia and Nigeria. And these people are the jewels of the crown. And on top of this, I have the privilege to interact and work with them on a daily basis. So today we will ask them to share their views on new countermeasures for fighting against global threats. And we will start with Dr. Chertidian, who will delight us with the adventure and the new endeavors of diatropics. Dr. Chertidian, the floor is yours.
Thank you very much, Xavier, for this for the introduction, and to Aisha. I'm really delighted to be here. As said Professor Peter Piot yesterday, 100-year anniversary we can only celebrate it once. So I'm really happy that IPD is celebrating it properly with our estimated guests and all these amazing colleagues. So today I'll dive a little bit into diatropics and how we are addressing the global health threats through portable and high-quality diagnostics. I like very much this graph. It's coming from the World Bank. It shows that the low-income countries suffers the most, have the highest burden of infectious disease. And most of these countries are African countries, as we can see here in purple. They have in the burden of communicable disease really associated to GDP, which means a country needs really to allocate enough resources in order to tackle and control the infectious disease circulation. Now, if I dive a little bit into flaviviruses, this is a graph, a courtesy from my colleague Dr. Gamufal from the virology department. And here we have data coming from the virology department, mainly the WHO Collaborating Center for Arboviruses and Viral Hemorrhagic Fevers, where we can clearly see here that many arboviruses have been detected between 2022 and 2023 in several African countries. And usually we have co-circulation of many of these. This means that we need proper measures in order to control them. For example, if you focus on a couple of countries, you can see that West Nile, yellow fever, and dengue are co-circulating. But how can you diagnose them? Sometimes they have the same symptoms. So you really need differential diagnostics, but with good tools. And just to highlight and to share that these data, as I said, are coming from IPD, which means samples are collected from countries and sent to IPD for diagnostics, which means delay in results sharing. Because usually we need a couple of days to do the testing. We do it by PCR, ELISA, sterilization sometimes. And sometimes samples arrive not in sufficient volumes, or they arrive completely destroyed because the cold chain is disrupted. So how can we do better? And I think there are solutions that I'm going to share later. Now looking at dengue in Senegal. Here I'm showing the evolution of dengue between 2015 and 2021, just in Senegal. For information, the first dengue cases has been detected in Senegal in 1970. It was a dengue 2 strain. In 2001, Dr. Ousmane Faye here published 2009 a nice paper on the circulation of dengue 3 in Senegal, mainly in Dakar, Louga, and Thiès. This was the biggest, first big dengue epidemic detected in Senegal. But as we can see here, the burden of circulation of dengue is really getting bigger and bigger from one year to another. And now we have a co-circulation of the three dengue serotypes, dengue 1, dengue 2, and dengue 3, all over Senegal. And this detection has been done by qPCR. But again, qPCR requires times, centralized laboratories, and high trained staff. And we also think that we can do better, even in Senegal. And my colleagues from the biology department and other collaborators came up with this brilliant idea. They developed a mobile lab in a suitcase, which combine efficient molecular tools, named mainly RP8 for recombinant polymerase amplification. And they in this suitcase, you have all you need in terms of reagents. Lyophilized reagents, you have the gloves, append of tubes, anything you want. And also a battery and a solar panel. But which is also amazing, they have these box where you can also manipulate highly infectious samples. And also, again, my colleagues here have deployed these tools to manage Ebola outbreak in Guinea between 2014 and 2016. So if you would like to know better about this tool, I recommend you to really read the paper from Jean et al., who used this instrument to detect dengue cases in some areas in Dakar. So here we are doing better because now we don't need to bring the samples from the lab, from the field to the lab. We have these portable devices. But again, we still need highly trained staff. In 2021, following to allow the evaluation of a high quality product, and for the first time in Senegal, we used a rapid diagnostic test to manage a dengue epidemic. We did it so with, again, Jen and other teams in Rosso. See, this test is a dual cassette. One cassette allowing to detect NS1, which is a good biomarker for acute dengue detection, and also another cassette, another strip for IgM and IgG detection. Of 70 samples tested in the fields, 26 were positive for NS1. And when we came back in the lab, of these 26 samples, 24 were positive by PCR, which means here we have a tool which allows us to really detect very quickly dengue in the fields, and we don't necessarily need to bring back the samples in the fields. And this is what I would like to talk today. How can we make sure that RDT will be of high quality, accessible, and affordable to the African market? Just before diving into that, this is a graph showing the measles circulation in Senegal in 2023. Senegal will almost reach an elimination phase of measles because there was vaccination campaign in 2021, but just 2 years later, we were facing massive measles epidemics. We had in just 2023 1,700 suspected cases of measles, 540 confirmed cases, and the cases were confirmed thanks to the work that we are doing in the surveillance systems. But all these cases were confirmed by ELISA. There is no PCR, just ELISA, which means, again, the samples need to come back in the lab, and this is, again, a delay in the result sharing. So, because we are developing a measles RDT, we collaborated closely with the Minister of Health in our Department of Public Health and the biology team just to deploy the prototype measles IgM test in the field, to train local workers and also generate some evidence. Here in red, you have the measles circulation in 2022, and in 2023, we have the measles. In purple, this is the measles circulation in Senegal, and you see a peak. We stayed in Touba for 2 weeks, and just during 2 weeks, we could see a peak of measles, which means with this RDT, we were able to detect more measles cases than the standard and conventional methods. And I think this is really a game changer in terms of how we deal with emerging or re-emerging infectious disease. So now I think I have convinced everyone that RDT is a good tool to manage infectious disease. And this is the reason why Diatropics has been created. We would like really to make this test available, of high quality, but our goal initially was not to compete with big companies, because we would like to focus more on niche products. So we want to develop tests that are not available for the African market, or tests that are available but not satisfactory in terms of performance. You know that very well a dengue product can work well in Europe or in the United States, but not very well in Senegal, in Africa, because of cross activities. And the third scenario where we would develop and manufacture a product is where the test is available but not affordable, too expensive for the African market. For example, Ebola. I think one of the tests deployed in DRC could cost up to $6. Why? Because the market was too small. And Diatropics' ambition is to really have
3 minutes.
3 minutes. Okay, is really to make this test affordable and the cost as low as possible. We are leveraging the lateral flow technology and are mainly working through international partnerships. So Diatrop is very demand driven, which means we are using the Netflix model, which is the model used for the hepatitis C, where manufacturers work with the buyers to supply a certain amount of products, which can be a drugs or a diagnostic here in this case, and the cost will be as low as possible because we have a visibility on the demand and volume, etc. So to go very quickly, these are the manufacturing processes of Diatropic. We can do end-to-end manufacturing of RDT. We have ISO 13485 certified by the British standard institutions. Our initial manufacturing capacity was between 2 and 4 million tests per year, but now it's transitioning to more than 50 million tests a year with a new facility that has been built in Bao that we will integrate in 2 days. And here we have some automation which give us more capacity. And the previous lab will be used for R&D and technological transfer. So this is a graph just to show that the initial focus were on NTDs and low volume product, but now with this big facility, so we have a unique opportunity to work on HIV and high volume products. And I think I have my friend Namal here, and this is something we are looking into, because we think that we can make HIV products at a very low cost and also of high quality for the African market. And also, obviously, we would like to work on any other products that can be relevant to the African market. So I'll stop here. This graph was just to show the overview of the middle product we are working with. These are products for IgM detection. There's also an NS1 product for yellow fever. This will be the first yellow fever NS1 product for the detection of acute yellow fever in the field. We are also working on a meningococcal meningitis RDT and also Ebola products. And I really hope that the portfolio will go bigger and bigger. But again, we need demand, and this is something we are looking into. So I'll stop here. And if there are any questions, I'll be happy to answer. Thank you.
Thank you very much, Dr. Chertidiane Diane. Now we will have the pleasure to listen to the talk of, I think it's Marie-Angélique, Dr. Marie-Angélique Sen, about running the Vaccine Research Center at the Pasteur Institute of Dakar. Thank you very much.
Yeah. Thank you, Xavier. Welcome, everyone. I guess most of our guests were already welcomed yesterday, but just as we say in Wolof, dal leen ak jàmm. So I will be talking about the challenges we face in the events of outbreaks and how we deal with it, specifically in the world of vaccine development. Just waiting for the slide.
Si on peut avoir les diapositives, s'il vous plaît, pour Marie-Angélique Sen. Merci beaucoup.
Okay. At least it gives you time to digest whatever Chertidiane shared with us already. There you go. So in the in the light of our celebration for this 100-year anniversary, I'll be talking about the direction IPD is taking to build on the legacy that came about these 100 years, all these departments that contributed to the reputation of IPD, and how these new initiatives are building from that and transferring that legacy to ensure a safer, or let's say a more sustainable future for our populations when it comes to health and response to outbreaks. So today I will be talking specifically of how in the Vaccine Research Center we tackle the challenges we face in Africa when it comes to research and development of vaccines. Just to introduce quickly the Vaccine Research Center and how it came to light, the goal is really to accelerate any kind of scientific discovery or innovation and make it a practical and accessible immunization capacity. We work really in bioprocessing, but also translational R&D to improve the efficacy, safety, and availability of vaccines, our focus being really diseases of local interest. So we have our manufacturing facility, maybe yellow fever or Madiba, that is in Jamniadio. Usually when there is a disruptive innovation, we try to avoid going directly to GMP. GMP facility, just turning the lights on is extremely expensive, and that will be reflected in the cost of the product you are selling afterwards. So it goes through us, meaning through more R&D, an R&D setting where we are a little bit, as I was saying yesterday, we are free to play with innovations, optimize them, and actually make it fit the context of our local capacity, and then transfer it to our folks in GMP. So the goal is really to de-risk tech transfers, to capture and maintain the know-how so that we build capacity and ensure sustainability, but also to enable continuous improvements for our GMP folks to do troubleshootings and so on. Well, I talk about innovation sandbox, but we still work within defined boundaries, mainly the scalability of our processes. We want to make sure that we can respond to needs when it comes to just routine immunization or pandemic response. Also, the financial resources, our projects are based on fundings that are available, of course, until we have a certain sustainability or certain autonomy to run our proper researches. The operational resources, vaccine manufacturing, IPD is still the only WHO pre-qualified manufacturer in the continent. So you can imagine that there are not many programs that teach manufacturing or bioprocessing in the continent. So we need to find a way to mobilize resources, to train them, to ensure that they become trainers, and then we maintain a sustainable pool of young scientists that we can leverage in time of need. And of course, regulatory and quality. Everything we try to make, we want to make sure that it goes from the bench to the arm of the patient. So we take into account regulatory requirements early on in our process of R&D. Think with our partners how we can adapt that or change it, or go from, for example, liquid culture media for cell culture to powder media that we can conserve and we can order bulks without risking it expiring too fast or not meeting the cold chain. And of course, the people we invest in through trainings and even sending them abroad via our partners so that they get a full manufacturing training. So the VRC is just a part of the whole ecosystem. What IPD has been investing on specifically to respond to that need for outbreaks and sustainability is to make sure that all the parts of the value chain is represented. Us, we are intervening at the early stage, from the discovery to preclinical. And then once we make that recipe for vaccines, we optimize it. Once it's done, we hand the baton to our colleagues in GMP for clinical grade manufacturing for clinical trials. And then once they are done, they go through the commercial team and transfer it to Madiba for commercialization. So there are all those steps that are going on into the lifelong of the product, if you can call it like that. So the VRC is built around different units that are critical. We have, of course, the preclinical part that is really at the end. We have the bioprocessing piece that is the heart of the VRC. Actually, we started with that bioprocessing unit. We made sure that it was strong enough, it was a good foundation, and then built the other units around it. We added computational vaccine design to reinforce the capacity of that bioprocessing capacity lab, and also QC and preclinical. Of course, we work with QA and the management in general. So when it comes to the challenges we face usually in R&D, I will just focus on the technical parts. I will not talk about supply chain or trainings and so on for the sake of time. So we do have limited infrastructures and resources, as I mentioned, the shortage of skilled expertise, the dependence on a lot of imports when it comes to pharmaceutical products, and the limited use of the genomic and epidemiologic data we have about the population that could help us actually design vaccines that are more tailored to our local population. And of course, the challenges of tech transfer that we face a lot and we try to adapt to. So the way we work through innovation is that we focus on the computational piece to use AI to help our designs and the manufacturing of our products. The bioprocessing piece where we optimize to fit the need of our local capacity. We use innovative platforms that are scalable based on the needs of the moment. So just to touch on those three parts, AI, bioprocessing, or the platforms we are using, and how we use innovation. For AI, we have a computational vaccine design unit that is really using those tools and data analytics to characterize the vaccines we are making, but also to help through the genomic surveillance data that are generated by our colleagues through these hundreds of years, define epitope conservations, how we can use that information to design the vaccines, and we are already using it for our first mRNA vaccines. And it's really that principle, using that genomic data, seeing how we can get those conserved epitopes, how we can optimize the vaccine to fit different variants, and then extract the sequence and use it for mRNA generation or any kind of vaccines. We also try to figure out the pathogen evolution prediction and the regional data utilization. Our goal is really not to leave any community not taken care of or not considered when it comes to these vaccines. And for the processing part, we invest in high throughput platforms, and we focus really on the bioprocessing piece, the first part that is more challenging. We invest on the Scalex platform. We have hydrocarbons and nitros, which allows us to be able to respond to needs based on the quantity of product needed. For example, the 31 you see there for MR, it can make more than 1 million doses in one run, which is quite impressive, and we can respond to challenges and to needs for quick responses. We also invest in mRNA platforms. We have the conventional manufacturing platform, more Moderna-like process, but also in semi-automatic platforms so that we can adapt to the needs. Some respond better to certain diseases than others. So we have a good range of tools that we can use in that aspect. One additional part that I just wanted to mention is the work we do also in innovation with cell engineering. We try to modify the genetic material of cell lines to produce more viral particles using functional genomics, and that allows us to tap into innovative technologies like CRISPR to actually delete parts of the genome and then test to see if we get the response we wanted. And usually we delete antiviral genes so that we increase the production of viral particles. And indeed, we got that increase from 70-fold to 87-fold, and it was tested with our industrial partners that were able to produce more than 3,000% of their initial, usually industrial range of production. So the outcomes that I mentioned here are really, we are trying to show, reduce the dependency on external partners to make sure that we get more sustainability, more sovereignty when it comes to vaccine manufacturing by developing candidates based on AI and using the information of our local population, using platforms that can be scaled up quickly or that are high throughput, and also making sure that we train our people and we have really a lot of expertise in the team. For example, my team right now is around 50 people. The average age is 31 years, and they are all skilled and trained in different areas to make sure that we maintain that sustainability. And just the take-home message is that we really try to reduce the cost of production so that we make our product accessible. We invest in thermostability for our remote communities, and our goal is to make sure that no community is left behind when it comes to fighting outbreaks and pandemics. So thank you for I'm saying thank you for my team, my whole team that couldn't be here, and we wanted also to thank all our partners that are working with us in those efforts and making sure that they increase more and we get more out of all these projects. So thank you all.
Thank you, Eric. It has been 10 minutes sharp. Thank you so much. Now I think we will move to Dr. Yahya Dieye, and he will instruct us about antimicrobial resistance in Africa and how to fight against this threat.
Okay. Thank you very much.
Yahya, une seconde.
Okay.
Je crois qu'il y a un petit retard dans les diapos.
C'est un point. Ça marche. Ok, c'est pas grave.
Merci bien.
C'est pas grave. Okay, thank you very much. So it's really a great pleasure for me to address you in this celebration of IPD century, and allow me to start my speech with some these two pictures. So this is IPD sometime during last century, so it's very old. I will not tell you where I am, but I'm sure some of the audience was not born at that time. So this is IPD in the 90s, and now this is really very emotional for me. This is a very nice colleague, good colleague we used to work with. Most of them have retired now. Some of them left us, unfortunately, and in memory of Dr. Jean-Louis Sartou, you can at the left, who used to be the head of the Department of Immunology when I used to be a technician in the 80s. So it's a very very long. And we use each year at the end of the year to do like to celebrate the year, all of us. And this is at the right. Most of the colleagues now are retired. So really, I'm very, very happy to have the privilege here to do this presentation. Although I was not continuously present at IPD, I was a few years in the beginning of my career in the 80s, and now a few years now. And it's also the opportunity to really congratulate Amadou for his great job. He really bring IPD to really a very, very high level, and I would like to acknowledge that too. So now coming back to my talk, which is antimicrobial resistance. Now, what is antimicrobial resistance? I think most of you know it. Is actually it describes the ability of a microbe to survive in the presence of drugs that are designed to kill them. Because we use drugs to kill microbes, because some microbes, not all of them, I mean, many of the microbes are very beneficial to us actually. And some of them are pathogenic, can cause disease and can kill. And we need drugs to treat these infections. And when these microbes become resistant, this is a problem, public health problem. And now, this is one of the most important public health problems worldwide, developed and non-developed countries. And this problem actually was anticipated by Sir Alexander Fleming at the left. And he's the guy who discovered the first antimicrobial used in human infection, and which was penicillin. And he was saying at that time that this is a sentence I took from his speech when he got the Nobel Prize in 1945. And he was saying that in the lab now, we can make the bacteria resistant to penicillin. And this happened also in the human body. And this is what we are living actually. And now, if you look at in the right, antimicrobial resistance is among the 10 biggest threats for public health. So this is a very serious problem. And I'm showing this because this is a study done by a group of UK scientists that was published, I think, in 2014 to 2015. At that time, they did a prediction because they were aware. I mean, we start being aware of the threat posed by antimicrobial resistance. And they were saying that by 2050, if nothing is done, 10 million of people will die each year because of AMR. And if you look at the picture at the left, you see the continent, the different continent, what is the burden in each of these continents. And as you can see, if you look at Africa and South Asia, these are the region of the world when the problem is the biggest actually, and it's almost 90% or more than 90% of the burden due to IMR is supported by these countries. Now, what can we do to face this big problem? And actually, we all know that if you wanna, the challenge is so big, the threat is so high that not a single laboratory, a single country, or a single institute can solve this problem. We need really to work together, and this is our philosophy in our lab. And I think in IPD, try to face the problem with our many collaborators, because this is a very serious problem. And what I'm going to present you is some of the work we are doing, because AMR is one of our most prominent program and projects at the microbiology research department at IPD. So I will talk about capacity building, which is try to train people to have the equipment, to have the laboratory that are well prepared to face AMR. We will do, I will talk about surveillance, which is trying actually to map where are the threats. Diagnostic, which is very important. Shafijan present some of the work they are doing. Also genomics, we had yesterday nice talk by Musa Moise at the IPD. We are fortunate to have a very nice facility to help us do genomic, and I will talk what we can do with genomics. And last but not least, alternative to antimicrobial, because if the antimicrobial are not working properly, we need some alternatives. Now, first of all, I should say, when I see the panel, I'm just like I'm the grandpa with this very young talented scientist. But don't worry, I will show you in our lab what very young and talented scientists are doing. They are leading the job, they are coordinating the job, and I will present some of them. So this is about capacity building, and we at our lab is doing what we call external quality assessment. This is very important, because when a laboratory tests a bacteria, test a bacterium and say whether it is resistant or sensitive to an antibiotic or antimicrobial, this is very important, because this result that is shared with the clinician. If you tell to the clinician that this bug is sensitive while it is resistant, this can be a disaster, because he will base his prescription of drug on these results. And that's why we need to do what we call EQA, in which we are testing the ability of laboratories to identify microbes, identify bacteria, test the antibiotics, and say whether they are resistant or sensitive. And our lab was selected in a project called EcoAfrica, in which we evaluate laboratories from 4 African countries, shown here in red. And this work is coordinated in our lab by Dr. Fatim Pouloli. She shared with us, in which we did this work from 2021 to up to now. And I'm showing you here just an example. At the left, what you see, each dot represents a laboratory. And you have this red line. All the dots that are above the red line are the laboratories that can give satisfactory results, meaning that they can properly identify bacteria and say whether they are resistant or sensitive, and when they say it is accurate. But all the dots below the red line are the laboratories that did not reach the threshold. And as you can see, about half of the labs did not reach that. It's really an issue. Yeah?
3 minutes.
3 minutes? Okay. But, okay. And this is the problem in Africa. In Africa, one of the problems we are facing is that we don't have enough microbial laboratory. We don't have enough expertise. So this is an issue. And to contribute to solve this, we have designed another project in the countries shown in green, in which we are going to evaluate, not only to evaluate the laboratory in these countries, but also build a network in order to work together to build capacity. This is for what we call surveillance. Surveillance is very important, but this helps us to map the threat. Where are the bacteria that can cause several diseases, and in the different sectors, in human, animal, food, environment, in order to look at the root of transmission and try to block it. And we are doing this with many of our collaborators in Africa and beyond Africa. Another work we are doing is a diagnostic. I will not elaborate too much on this. So this is actually a portfolio of projects in which we are working on diagnostics. This project coordinated in our lab by Dr. Shafal. He's here with us also, and we are, of course, collaborating with IPDs, the sequencing facility, diagnostics. The goal is to build diagnostic tools that can rapidly identify the bacteria and identify also the resistance. As for genomics, I'm showing here just one very important result we got when we start doing genomics in bacteria. The primary goal was to use genomics in order to find the genetic determinant of resistance. And what we find actually, we were analyzing infection by Salmonella. Now, Salmonella is a bacterium that causes two types of diseases: gastroenteritis, that is very often mild, resolve after a few days, and invasive disease that can be fatal. In 20% of the case, it is fatal. So what we found here is that when we analyze the isolate from diseased person, in the community, we have isolated by doing outbreak investigation, we are isolated Salmonella that cause gastroenteritis in the communities. And when we compare this Salmonella to Salmonella that we isolate from patients suffering of sickle cell diseases, which is very common in Africa because it touches black people, we find that actually what we are to make it short, we find that the same bacteria that cause mild gastroenteritis in healthy people cause invasive fatal diseases to sickle cell disease patients. So this we were able to find this by doing genomics. So this is very important because we have by applying genomics, we have identified some very serious threats in our communities. So this work is coordinated by Dr. Shah Ibrahim Lo. He's currently not traveling. And last but not least, this is the alternative to antimicrobial because the resistance is growing all over the world. So we need alternative to antimicrobial. So I'm just showing here 3 projects we are working on. The first one at the left is a recent achievement by Isanjay. He's finishing his PhD in our laboratory. He developed a system in which he isolated phages from wastewater and shows that these phages can kill multi-drug resistant bacteria. So this is really very nice result that need to be analyzed further. And then in the middle we have Dr. Mapenda Gai. He's a postdoctoral researcher who joined us recently, and so this is a very, very interesting result because he isolated some molecules from environmental sites, and he demonstrated that these molecules also are effective against multi-drug resistant bacteria. So this is very interesting results that we are working on to push it further. And in the right, Dr. Sohna Nango also, who joined us recently, she will be starting soon a project on probiotic, because probiotic actually are beneficial bacteria. And as you know, the field of antimicrobial research is very, very active, and one of the ideas is to use beneficial bacteria to fight pathogenic bacteria. And she's an expert in what we call culturomics, because as you know, many of the bacteria that exist cannot be cultured in the lab, and she has worked on a system to be able to culture this bacteria in the lab and identify probiotics that we can use as alternative to antimicrobial. So as you see, many young, very talented researchers that will be doing the work, and I'm sure that we'll have very nice results in the future. So this is what we try to do. We try to mobilize our energy with our collaborators and our partners in order to find solutions to prevent, detect, and treat bacterial diseases and antimicrobial resistance. So I'd like to thank all our labs. So these are very nice people who are actually doing the job. I'm just here, the old grandpa coordinating. And thank you to all our funders and our partner in Africa and beyond. Thank you.
Thank you, Dr. Dieye. Your enthusiasm is infectious. And now, last but not least, we will have the pleasure to listen Dr. Lati Tiamgay, who will talk about malaria vaccine design.
Thank you. So I must acknowledge that it's tough for me to stand here after these very insightful talks, and I know that the bar is already placed very high. So I'm trying to match and see if I will reach the level. So I think no. I think the slides is not precise. No.
So apparently a little problem with the slide. We are kindly asking a minute of patience.
Hmm? We Sena? Sena credit protocol. Okay. Menos profesi agora se abre Merci. All right.
Thank you very much.
All right. So thank you very much. So as you can see, my talk is about leveraging field-based investigations to inform structure-guided malaria vaccine development. So as you know, and there is no need to highlight too much on this, malaria is bad because killing hundreds of thousands of people every year, and the highest burden is within West Sub-Saharan Africa, and we still face the growing threat of spreading of resistant mosquitoes and parasites, which makes the battle against malaria more challenging than ever. But there is still hope in fighting malaria because the parasites offers us too many space or too many stages where we can target it to try to combat it. And here you can see some of the main stages of the parasite we can tackle by designing either parasitic vaccines, which will prevent the disease, transmission blocking vaccines, which can block the transmission between the vector and the human host, but also the blast stage vaccines, where I'm going to focus my talk on. So as you can see here, this is the latest update about the malaria vaccine portfolio as of March 2024 by WHO. So I want to draw your attention into the highlighted box here in red about the number of vaccines that have been registered so far in against malaria, and of the this number, only 2 have reached phase 3 to 4 clinical trials. And if you look at the targets, so 61 of these vaccines targeted target the labor stage of the parasites, and only 2 of them have been approved. I will come to that. And the blood stage I'm targeting on here, we have 64 blood stage vaccine targets that have been investigated so far, but none of them have been approved. So regarding the circumsporozoid protein antigen, which is the major protein expressed by the liver stage, we have 2 vaccines that were approved, which is the RTSS and the R21 that were recently approved by the WHO. But there's still room for improvement because data from the phase 3 clinical trial of RTSS have shown that this vaccine protects only 1 child out of 10 vaccinated, and the global efficacy after 4 years follow-up was 40%. And this is mainly due by the fact that this vaccine provides a strain-specific immunity, which is associated to a short-lived protection. So the question would be, why is it so difficult to develop a vaccine against malaria? So there are so many reasons. One of them is that the parasite has a very complex life cycle, but also a huge genome which expresses or encodes nearly 60,000 genes. And these genes are expressed differently between the stages. And the issue that has been raised is that most of the vaccines that are being investigated were based on laboratory lines that have been maintained in culture for decades and thereby have lost all contact with the immune system and were not reflective of what's happening with the clinical isolates. So you can see here on the bottom of this slide the different mechanisms that can challenge vaccine development with the variability that we observe in the parasites. So here is our goal within our G4 group, where we want to assess the impact of genetic diversity at the very early stage of vaccine development and use this information combining genomics and structural biology to design better vaccines based on structure guided vaccine designs. So this is our kind of goal. And to this presentation, I'm going to talk about one of the main complex that we are looking at among many of the antigens that we are investigating. It is the complex made of 5 antigens called the PCR-CR complex, which is the PTRAMP, CSS, SIRPA, RIPA, and TFRH5. So when you look at the invasion process, it happens in 4 steps. So the parasite will first enter into contact with the RBC through an attachment and then reorients itself to oppose its apex into the red blood cell, and then where it will deploy now the invasive mechanisms to invade the red blood cells. And one of the key antigens used here is RH5, which is essential for parasite survival. So you won't have the risk of immune escape, which is highly conserved, but also is able to trigger immune response against the parasite. So what we did here is that to know at the very early stage whether this vaccine is going to work or not, we started investigating the impact of genetic diversity from phase 1 clinical trials. So the data I'm going to present here were generated using antibodies that were generated from a phase 1 clinical trial using the Symposium adenovirus and the MVA regimen, where participants were vaccinated at day 0 and 28, and then PBMCs were isolated at day 26 and cryopreserved. From these isolated PBMCs, we did antigen-based or antigen-specific cell sorting of the memory B cells that were used to express the variable heavy and light chains of the antibody-producing genes and clone into bacteria and express to produce monoclonal antibodies using the hex cells. And these monoclonal antibodies produced were used now to test their efficacy on clinical isolates that are infecting people living in an endemic area, namely in Kédougou here in Senegal. And here is the strategy, the workflow that we follow here. So these antibodies were incubated with the parasites for a life cycle, which is 48 hours. And upon reinvasion, we assess the reinvasion rate using flow cytometry, as you can see on the right hand side of this figure. So after generating the data, we analyze it to see what was the inhibition capabilities or intensity that we observed. And we can see here that the parasites were highly inhibited at a dose-dependent concentration, where we use the maximum dose of 150 microgram per ml, and we can reach up to 80% inhibition. And here the nice thing is that we can have a very consistent inhibition between clinical isolates, which are reflecting what is happening in the field, and the laboratory lines, which we are using as a model in the lab, which is a very good results here. And we can see here, when we look at the heat map, we can classify our antibodies into three main groups: the GIA high, which can inhibit up to 80%, the GIA medium, which inhibit between 40 to 60%, and the GIA low antibodies, which inhibit the parasites less than 40%. So, but we can see here that there was one strain, which is the 413, which is very low inhibited by all antibodies, and we did not know why this happened. So based on these results, we decided to see whether there is any match between phenotype and genotype of these observed phenotypes that we are seeing here. And we can see here from our inhibition data, when you look at this particular antibody inhibition, all the parasites were inhibited except one, which is the FVO, which is a lab line. And this is because this FVO has a mutation at the epitope binding site of this particular antibody. And this is the laboratory line. So we do not want to have this experience with our vaccines in the clinical lines, because this will cause selection mechanisms where parasites will be escaping the vaccine derived antibodies and will be causing disease, and you might end up having a vaccine that does not work. So what we did next was to look at the prevalence of SNPs in our populations here, and we could identify 15 SNPs here present at different prevalences but also at different frequencies. So a striking observation here was that the wild type allele that we used to make our vaccine was indeed minor in our population, meaning that most of those parasites circulating do not match the vaccine allele, but still we have inhibition in these parasites. So here is the prediction of the different mutations that we found, and we can see that the parasites, these mutations can impact the antigen in different ways. They can affect the binding of the antigen with the antibodies, or the binding of the antigen with its receptor on the red blood cells, or alter the structure, which can ultimately alter the binding sites of the most potent antibodies. So what we wanted to see now is, okay, these are monoclonal antibodies, but when you vaccinate people, you generate a response which is polyclonal. How do these polyclonal antibodies interact? So we wanted to see whether there was any synergistic or additive interaction between these antibodies. And we come across of this antibody, which is a R11, that is not so much inhibitory on its own, but it will slow down the invasion process, because something I did not highlight is that this process happens within 30 seconds during the invasion. But when the R11 bound, it will lengthen this process, and it goes up to 2 minutes. So it gives room to more antigens, more antibodies to bind. So we can see here that when you add R11 to the low inhibition antibodies, it will increase the inhibition pattern. But what we wanted to know is whether this increase is indeed synergistic. And we use this formula to calculate whether it was synergistic or antagonist. And we see here that most of the antibodies we saw, this interaction was either additive or synergistic, but in some cases we have antagonism, meaning that the combination of these antibodies might not be the best for forever. So here I'm presenting another set of data by Dr. Mariama Nicole Puy, which is looking for the
1 minute.
Yes, for the other antibodies, SIRPA and RIPA. And you can see here that these ones present low to intermediate inhibition as compared to PFRH5, which is the main target. And you can see it here. But when you combine antibodies between them, you can see that there is an enhanced response in terms of inhibition, meaning that the antibodies, though they are low inhibitors, they can synergize together and have a higher impact and a higher inhibitory activity in the parasite. And this work is still ongoing, and we are moving forward to assess the whole pentameric complex in our next assess. So this is what our impact will be. We are trying to translate scientific insight into vaccine discovery and design using the structure-guided results to better design vaccine candidates and also move to epitope focus antibody design and discovery. So with that, I would like to thank you for your attention.
Thank you very much, Dr. Latig Gaichamgai. Sorry. So you have told us very compelling and exciting scientific stories, but we would like to take you outside of your comfort zone. And first of all, we would like to understand, why did you return to Senegal? Why did you reduce your salary? Why are you facing everyday hurdles, problems, stuff? What is the motivation? I don't know who would like to start.
Yeah, Xavier, indeed. It's a question out of our comfort zone. So I can start. I think I left Senegal when I was 18 and I came back, I was 30, 32. I spent a long time abroad, and I think at some point you just want to go home. I think this is a reality that we have all faced. But also you want to contribute, but really have a very strong impact. I could see that what I was able to do when I was in France, I had many colleagues that were able to do it. But in Senegal, we still needed to reach a certain level in terms of technology. And that was a main driver for me to come back. And today I can say I don't regret. I don't regret coming back because I can see what IPD's ecosystem has offered to me, and I'm very happy to be here.
Thank you very much, Marie-Angelique.
Yeah, I'll try also. Well, for me, I always wanted to come back, but at that time, my field was quite, let's say, special in the sense where there weren't many people doing nanotechnology out of Asia. Even in Europe, it was hard to find. So it was sure that I couldn't come back unless I set up my own thing here. I would always call my mom, okay, mom, when do you think I can actually make it back to Senegal? Until I switched to vaccines. At that time, I think when COVID started, when I was in Canada, the lab I was in was among the hundreds labs selected to develop candidates for COVID. And in our lab, we were developing 4 candidates at the time. But I was honored, but my worry was nothing is happening in Africa. What about my family, my neighbors? When will they get a job? So it was more and more I wanted to come back, but there weren't any ecosystem. So as soon as Madiba was set up, as soon as our authorities realized that we needed sovereignty, it was a no-brainer for me. So it was, okay, I need to pack my bags and go back. And it was the same for my team too. As soon as they heard about these initiatives where we can do vaccine development and so on and so forth, for them to, in less than a month, almost all of them are already in Senegal. So yeah, it was just waiting for the opportunity or the ecosystem that allows us to contribute and to thrive here.
So you have created the first avalanche in Senegal. Yes, ma'am. Thank you, Marie-Angelique.
Thank you for the question. Actually, I did not came back to Senegal because of science, obviously, because when I left Senegal, actually before leaving Senegal, I was almost 30 years old. I worked at IPD, and at what point I didn't want to continue my studies. I went to France. I got a PhD. I worked in the US and worked in Australia, Malaysia, and at what point I really feel that I really miss Senegal too much. And another thing was that I did not really want my child to grow far from Senegal. Really, at one point I didn't feel happy in all these countries where I was, because if I try to understand, maybe I was raised in a very, very traditional families, African families. And now I'm trying to convey this value to my children. It's very difficult. Senegal has changed completely. And after spending 20 years far from Senegal, I really needed to come back. And that's why I came back. Yeah. Thank you.
So thank you for making Senegal great again. Latin.
Yeah, thank you. I think for me, I've not spent too long out of Senegal because I think it was only 5 to 6 years during my PhD, and there were two main reasons why I came back. One is that the disease on which I'm working, I think to do impactful work on malaria, you need to be on sites where the disease is prevalent to see exactly how your research can impact the reality you are seeing every day. The second thing was I didn't want to betray our philosophy. During my training, I was in Ghana where I did my PhD, and the philosophy there was we should rather bring the expertise from outside and keep them in Africa instead of training scientists and sending them home out of Africa. So that was something that really was keen to me. And when I got the opportunity to come back to IPD, among other opportunities, and I did the comparison with my career vision and perspectives, I think that it was the right choice to come back, though it was challenging. But so far, I think I've not regretted, and I don't think that I will regret that choice coming back. Yeah.
Thank you very much. We have a scientist, we have a philosopher. We are very lucky. So now I would like to go to the second round of questions about, so you described the threats you are fighting on a day-to-day basis, but beyond the disease, beyond the pathogens, what are the threats to your existence, to your ambition, to your projects? What are the things you would like to change in the future?
I can start on this one. And this is really from my experience. You know, when you work in developed country, I worked in developed country for 20 years. And when you come back to Senegal, you can make a comparison. You can say why these people are so advanced and why we are not that much advanced. And when I discuss with friends and colleagues, I say, if you look at Senegal, are very smart people. If you compare the average Senegalese to an average American, to an average Malaysian, Senegal are very. Why we are not so advanced? And I think one is really the management, the organization, and I'm not very happy to say that. I think that we need to put more ethics in the way we work. I think these are things that I think that if we change this will push the country very, very, very quickly. And I think that I'm very happy every time I see young people coming back to Senegal because they bring what they learned, what they were in country where things work. And I think when we reach a critical mass of these people, things will start changing really. So this is just my opinion.
Thank you very much. Yeah. Very impacting.
Yeah. For me, I see two threats. I think the first one is not understanding the market very well. So now we have a new commercial direction, which is really doing an amazing job so far. But I wouldn't want that to develop a product for which the market wasn't well very understood, which means there will be a need but not much demand. I think this is the first threat I see. The second one is really losing track with innovation. We know that the IPD is very much towards innovations. Now we are talking about RDTs, AI, many things. But we need really to keep the momentum because what is true today can be very obsolete tomorrow. So I think that's a fact.
Thank you very much.
Yes, I'm joining what Dr. Yahya was saying in the fact that people are really smart here. We have a smart population. They know what are the issues. They generally know how to deal with it, but they don't have the tools. So one thing we are dealing with, which is a challenge even within what we do in vaccine research, is first Afro-skepticism. When you say that you are doing a project, depending on where you say you are doing it, it doesn't have the same level of response. In Europe, you say, okay, that's classic. In Africa, they will say, can you do it? And so our team have to face that on a daily basis and actually have to always prove ourselves, showing that actually we are capable of doing it. It's not because it's happening in Africa that it's not possible. Africa has the potential to do so. They just need the tools to do so. So that's one first challenge we have. The second one I would say is how the mentality we grew up in. It changed with the generation. Now this new generation is taking ownership of how they are portrayed, and they are taking ownership of what they can achieve for their communities, which wasn't the case a few years ago or a few decades ago. So that is really important for people to empower themselves, not wait for others to empower them, but to empower themselves and believe in themselves and believe in the fact that if they have the motivation to and the vision to contribute to their communities, they can do it. They shouldn't let's say, be blocked by how they are perceived, and actually change that perception of what people have of them, or what other communities have on them as African scientists, or in this case, Senegalese scientists. And they have something that they can bring to the table. Sometimes how you are brought in, the community or the environment where we grew up in, is really valuable when it comes to innovation, how to think outside the box. And they need to really take that for them. It's granted, it's their skills, it's what they bring to the table and contribute to the global efforts.
Thank you very much. Excellent. Lati?
Yeah, I think for me, the biggest threat will be losing track and also losing self-discipline, because they've said it. Senegalese are very smart, and with the way technology is going, if you are not focused and disciplined, you might be tempted to do everything. But that should not be the case. We should identify the key challenges and see how we can impact and focus on one thing at the time. And I think if we are not careful, we might lose that self-discipline, and that is something that I'm always trying to discipline myself about, because I'm always tempted to do new things. But when I remember that I have things that I've started which are not yet completed, it brings me down again, and then think what is the most impactful. And I think this is something we also should consider with our knowledge, our like how smart we are, and all those innovations that are going around. Yeah.
Thank you very much. So ethics, Afro-skepticism, focus, return to home. Thank you very much for this sharing. Since we have a lot of young people in the room, including Rino, Amadou, Solomon, Rebecca, I would like you to finish with a one-liner legacy for the young people and inspire them. Thank you very much. So what would you come up with, Cher Diane?
Yeah, so I think I would recommend to stick with resilience.
Stick with resilience.
Yes.
Okay, thank you very much. Yahya?
I really like the presentation this morning by Marco. Really, really let your imagination go wild. I think that this for the young people. You can do a lot of things. So guys,
Marie-Angélique?
Yeah, actually building on that, it's really not only letting the imagination go, but really believing in what the impact they can have. They can think that it's really insignificant, but it's a huge deal when it comes to paving the way for sovereignty for our continent in general.
Thank you very much. Lati, to conclude?
Our message will be self-awareness. Know what your strengths are, and what are your weaknesses, and work towards having a balance.
Thank you. You really make me feel young, so thanks for these guys. Thank you to all.
thank you, David.
Thank you to our repats, like Xavier said, who we have seen are all thriving in their various niches, despite all the obstacles that they might be facing. We've had a very great session today where we've learnt new countermeasures and the directions that the IPD is taking to ensure a more sustainable future for outbreak response. We've had very informative presentations, and we've heard from Cheikh Tidiane Diagne, Marie-Angélique Sen, Lati Cham, and Dr. Yahya J. I would like to take this moment to congratulate each of you for the groundbreaking work that you are all doing, and your teams as well for their passion and their drive. And also to thank you all for giving your teams and the next generation the space to think and dream and imagine widely, like Professor Marcus said. If we can all please give them a round of applause, our speakers and their teams. And now I will give you the directions for our break. We'll be back in the room at 2:00. We will start at 2:00 sharp. We will go out for lunch for the next hour and a half, and see you and enjoy the lunch. Thank you. Italy. He is also Honorary Professor of Vaccinology at Imperial College London and Senior Professor of Molecular Biology at the University of Siena. His prior positions have included Head of R&D and Chief Scientist at GSK Vaccines, Head of Vaccine Research R&D at Novartis, CSO at Chiron Corporation, and Head of R&D at Sclavo. He's earned his PhD in biological sciences at the University of Siena in Italy and was visiting scientist at Rockefeller University and Harvard Medical School. Dr. Rappioli is an elected member of the U.S. National Academy of Sciences, the American Academy of Arts and Sciences, the American Institute for Medical and Biological Engineering, the European Molecular Biology Organization, the Royal Society of London, and has received several awards, including Gold Medal by the Italian President, European Inventor Award for Lifetime Achievement, and the Robert Koch Award. He has introduced novel scientific concepts, genetic detoxification, cellular microbiology, reverse vaccinology, developed licensed vaccines, the first conjugate vaccine against meningococcus C, conjugate vaccines against meningococcus ACYW, MF59 adjuvanted seasonal and pandemic influenza. This was the first vaccine adjuvant approved for human use after the aluminium salts. Dr. Rappioli is founder of the GSK Vaccines Institute for Global Health and is among the world scientific leaders who are dedicated to the sustainability of global health. Please help me welcome Dr. Rino Rappioli.
Okay. Well, thank you. Thank you for the introduction. And thank you, Amadou, for inviting me here. It's a really pleasure. My first time here in Dakar. Although I've been hearing a lot about it, I'm still curious to see beyond the hotel, which is beautiful, but I would like to see more about the Institute. And so my goal is basically to give you an idea about how vaccine research and development basically changed the last few years and where it's going. So if I can have the first slide, I'll try this. Anyway, while the slides come up, basically what I'll do, I'll review the changes that maybe I need to do something. No? So basically, I'll review how the vaccine field changed during the last 20. Okay. Yeah, I'm doing something well.
Hi again. We will just have a brief pause of a few minutes. We have a little technical issue, so you have more time to the break. I give you 3 more break minutes. Yes, and in the meantime, if you have any questions, think about it, and we can ask Dr. Rappioli later. Thank you.
Okay. Well, sorry about the technical problem. Apparently the slides through e-transfer went to one place but not to the other one. Anyway, basically I'm going to talk about the kind of revolutions the vaccine development that happened during the last 30 years, 40 years. And when I talk about vaccines development, basically I talk about the technologies that have been used to make vaccines. And here I basically a summary of all the technology being used to make vaccines. At the bottom you see the empirical approach, which is the one of Jenner, the one of Maurice Hillman, live attenuated vaccines, kill vaccines. Basically when you make vaccines, you have to have bacteria, viruses, and you kill them or attenuate and inject them. But then in 1980s started to have new technologies. The first one was recombinant DNA, then glycoconjugates, then genomics, reverse vaccinology, and then you have an explosion of new technologies, at the top of which is artificial intelligence, which is a very new coming up into the field. And basically all these technologies, basically every new technology allowed us to conquer new diseases. So things which are impossible, like at one moment, then become very easy once the technology changes. So I'll start from, I will not talk about recombinant DNA or glycoconjugates. I'll start with reverse vaccinology. So I'll do reverse vaccinology, structural vaccinology, synthetic biology, and artificial intelligence. Basically, these are the things I'm going to talk about. And start with reverse vaccinology. To give you a background about this, I was working on meningococcal vaccines early 1990s, so 30 years ago, 35 years ago. And we're making vaccines, successful vaccines for meningococcus A, meningococcus C, meningococcus Y, and W. But we're not able to make vaccines for meningococcus B. Conjugates didn't work. People tried with genetics, purified proteins, purified polysaccharides, purified LPS, nothing worked. Everyone wanted to make a vaccine for meningococcus B, no one has succeeded. Our lab also tried, it didn't work, and so basically at some point I stopped the project in our lab and said, we're not going to do something we cannot make. We did not have the technology to solve the problem. So I said, we'll stop the things, but the medical need was still important. So we said, in case a new technology, revolutionary technology comes, we may go back. At some point, 1995, Craig Venter published the first genome of a living organism. It was a bacterium. And that was clearly a new technology, a revolutionary technology. The first time we saw the blueprint of a living organism. So we started immediately to say, well, if we had the knowledge of all the genes of this bacterium, maybe we could find genes that would code for antigens for a vaccine that we've never been able to find with traditional technologies. So at some point I went to visit Craig Venter, and I managed to convince him to sequence the genome of meningococcus B. And basically, you see, he's in the top there, and he was sequencing the genome and putting the sequence in the computer. I also needed someone that would be able to help interpret the genome. That was Richard Moxon at Knoxford. And then we did what we were good at doing, trying to make vaccines out of that information. And so the outcome of that was we got the genome of meningococcus B. We asked the computer how many genes will code for proteins that potentially on the surface of the bacterium, because we wanted to have something that would be reachable by antibodies. And the computer said 600. Then we started with 600. We wanted to express all of them. We succeeded only with 350. And then we immunized 350 groups of mice with individually purified proteins. And then we started to test them. And it was amazing because in 6 months, we were able to discover 91 proteins on the surface of the bacterium never described before. And just to give you a context, all microbiologists from the beginning of science to the moment that described 12, 13 proteins on the surface. And now in 6 months, we got 91. And then we basically started to get which one of the best of the 91. We found 28. Out of the 28, we selected 3, and those 3 were made in a vaccine, which is now licensed in like 50 countries of the world, and basically is working. And this was something which is an impossible vaccine, became possible because of new technology. Now, obviously, this was 30 years ago. At that time, it took Craig Venter 14 months to do one genome. And you know, today you can do hundreds of thousands of genomes per day if you like. The other thing I want to mention is structural vaccinology. And I mentioned that through respiratory syncytial virus. Now, you know very well respiratory syncytial virus is a normal virus. Every child, most of the hospitalization in high-income countries in the first 6 months of life are due to this virus. Most of the mortality in low-income countries the first 6 months is due to this virus. And the virus was known already in the 1960s. And you see on the right as these proteins on the surface, in this case called F protein. The amazing thing is that the first vaccine for RSV was made in 1967 and was a complete disaster. The vaccine was made by the way they used make vaccines at that time. They purified the virus, they inactivated formaldehyde that they injected. Unfortunately, that vaccine made the disease more severe in the children that got the vaccination. So that was a big failure. Since 1967, there have been 50 years of failures. The last one was 2019. And for 50 years, we tried to make vaccines, we completely failed. The reason you will see in a moment is the reason was that we had no idea what we were doing. And the reason is the following. The things we didn't know was that we know that on the surface of the virus there's a protein. The protein is called F or fusion protein. What we didn't know is that you see on the top, on the left, you see the structure of the protein is a trimer on the surface of the virus. In the conformation that we call prefusion, in the right, you see the same protein. Now, once the virus entered the cell, which is called postfusion. Now, what we didn't know is that the prefusion is absolutely unstable, but really unstable. Basically, you are very careful, you purify, you think you have it, you go get a coffee, you come back, it's gone. And basically, the other thing we didn't know is that the protein on the left, the prefusion, is absolutely a good vaccine. The one on the right is absolutely a bad vaccine. Actually, it's not a vaccine at all. Now, for 50 years, we thought we were working on the protein on the left, but in fact, we were injecting people with the protein on the right. So and we didn't know all this until in 2013, Jason McClellan, Barney Graham at the VRC, basically they managed to get an antibody from a Chinese group that will basically freeze the protein on the conformation on the left. Out of that, they made the crystal structure, and you see the crystal structure on the left of the prefusion, the crystal structure on the right of the postfusion. And below, you see the structure of the monomer. And clearly, the monomer on the left is the one that you want to have in vaccine. The monomer on the right is the one you don't want to have in a vaccine. But you know the monomer on the left is absolutely unstable. So now that you know the structure, what do you do? And I did this test with my 5-year-old grandchild, and he actually got very close. Because look at on the right, the 2 red amino acids. They are very far apart. On the left, they are very close together. So if you don't want this to happen, what you need to do is to put a glue. That's what my grandchild said. I mean, put a glue there, these 2 amino acids. And the glue, Jason McClellan, was let's change those 2 amino acids in cysteines. They made the disulfide bridge. It's done. Now, this was an impossible thing for 50 years, 50 years of failure, and now my grandchild can solve it. And the reason is that now that we know the structure, it becomes easy. But before, it was absolutely impossible. So that's the potency of the structure of vaccinology. But Jason McClellan wants to solve that. Out of that discovery, there are all these vaccines are approved in 2023 for RSV, which are on the market. Basically, the RSV problem is technically solved now. Vaccines are licensed. But Jason McClellan, basically, after solving the RSV, in 2017 was doing something nobody else wanted to hear about. Was working with an obscure virus called MERS, which is a coronavirus from camels that in Saudi Arabia from time to time jumps into humans and kills someone. But we've been discussing many years whether we should make a vaccine. Nobody wanted to do it. It's too small population, no market. So basically, Jason McClellan was doing science and working with the coronavirus. And basically, at some point, they were using cryo-electron microscopy. And out of the spike of this coronavirus, basically found that you see on the top, some of the proteins were elongated. Some of the proteins below there are globular. So, maybe if you want to make one day you want to make a vaccine for a coronavirus, maybe the coronavirus have the same problem as RSV. They have a pre-fusion and post-fusion, and you better have a pre-fusion conformation. So basically, this time, you see on the left, you have these two alpha helices, which are more or less like this. And in the post-fusion, they become like this. So this time you say, well, the way to avoid this change is to put a proline between these two alpha helices, because that will freeze it. So he published this paper in 2017 saying if one day you happen to make a vaccine for coronavirus, keep in mind that if you put a proline there, it's going to be better. 2017, nobody could care less about a coronavirus vaccine. And so the paper, nobody noticed the paper. But in 2020, when COVID arrived, this was the solution used by everybody. Again, the potency of structure-based vaccine. And now, Jason McClellan found a way to do these things by using his basically intuition to make changes. But now, with the AlphaFold, Nobel Prizes that have been given to basically David Baker and all the others, basically, once in this interview to Science, basically, they asked David Baker, what do you want to do with your now Nobel Prize? You got this huge discovery. So I want to do better vaccines. And that's actually true. Because today, if you want to stabilize a protein, you don't do anymore what Jason did, put a disulfide bridge, or you do a proline there. You ask the computer how to stabilize a protein, and the computer will tell you solutions that you can never dream of, because the solutions we have found are the ones that are very visible. The computer finds things which are very minor, but altogether they're much stronger than the ones that we find. So today, we'll never touch a protein and stabilize a protein without doing that. So now I'm going to talk about how we move to synthetic biology. Now, to do that, I need to go back to 2009. 2009, if you remember correctly, maybe the young people don't remember anymore, we had another pandemic, was a swine flu. And this swine flu happened early March. And as soon as the virus was in Mexico and southern United States and killed several people, and then basically we manufacturer at that time was working for Novartis. They asked us, you need to make a vaccine. The way to make a vaccine in 2009 was you need the virus. The virus was there in southern Arizona and Texas, United States. Basically went to CDC. The CDC had to basically make reassortants that will allow the virus to grow in eggs, because we manufacture the vaccine in eggs. And we started to make a vaccine. And in 4 months, we had the vaccine. You see the red line is the millions of doses of vaccines. And we started to make a few million, 10 million, hundreds of millions. And we're very proud because in 5 months, we were in the hundreds of millions of doses of vaccines. But it was very disappointing because you see the dark line, which is the incidence of the virus had peaked at 6 months. And basically, when we had a lot of vaccine, it was too late. So the message out of this was 5 months are not enough. Need to go faster. So in 2011, 2012, 2013, the mindset of everyone working on vaccines at that time was we need to go faster. Now, the way to go faster happened on Easter Day of March 31st, 2013. This time, the Chinese Center for Disease Control put on their website the sequence of 2 genes of a new virus, avian influenza virus, H7 and 9, and all the predictions was that this virus was supposed to be the next big influenza pandemic, the avian one. Everybody was waiting for that. So basically, the race started again. We need to make a vaccine. We need to go faster than 2009. The problem was the virus this time was in China, was not in Texas. So basically, it took 2 months from China to Central Disease Control. So at that time, I was still working with Craig Venter. In the meantime, he had become very strong in synthetic biology, making synthetic genes. So we decided to make a totally different approach. And in 1 week, we had 2 different vaccines. One, a conventional vaccine, and one was made of RNA. And the way we did that was basically on Monday morning, Craig Venter in San Diego basically downloaded the sequence from the internet and started to make synthetic genes, neuraminidase and imagglutinin. Monday evening, put those 2 synthetic genes into the express mail. Tuesday morning, the 2 synthetic genes reached our labs in Novartis in Boston. And we started to use the 2 synthetic genes to make 2 types of vaccines. The one on the left to use reverse genetics to make a virus, to make a conventional vaccine to be grown in eggs or in mammalian cells. The one on the right was an RNA vaccine. By Saturday, both vaccines were ready to go. And this was 7 weeks before the virus reached Central Disease Control in China. So my postdoc at that time made this slide. Basically said, well, so far we've been thinking about sending virus here and there, across customs, across the dangerous things. So why are we shipping viruses? All we need is to ship sequences. They don't go through customs. They don't have all these regulations. They travel at the speed of light. And basically, you can redo everything there. And that was the moment where I thought basically we were transitioning from what I call analog vaccines to digital vaccines, because analog vaccines are the ones we used to have. We need a real virus. You need a real bacterium. You need a real stuff, a recombinant something. With digital vaccines, what you need is the sequences. They travel to the internet, they do a computer. A computer basically, with or without the help of man, can design a vaccine and transfer the information to a robot, and the robot can actually make a vaccine. So, and that brings me a little bit to science fiction. So I'm thinking about tomorrow, not the distant tomorrow, basically where you have this process. Now you have everything that pops up everywhere in the world, the sequence on the internet, the internet brings the information to the computer with or without the help of man designs the vaccine and sends the information to many robotic stations. There are full of them in Africa, full of them in Latin America, Asia, and this. So basically you can have local manufacturing, mostly completely robotics, done. So that will solve a lot of the problems of manufacturing we have today. But you can also think another thing, that's the science fiction, that in 2050, we're going to have the colony in Mars. And now, if you have an outbreak there, if you want to send a vaccine, by a spaceship is going to take 9 months. That's too much. But if you send the information through the internet, basically it's going to take only 48 hours. And if you have a robotic station, there the vaccine is done. So that solves also the problems of the future. And this is obviously science fiction, but from my point of view, the science fiction is actually the colony Mars. In terms of vaccines, I don't think we are that far away from doing this. I mean, the only thing is that things are not yet completely done by computer. We need human help. But the robotics of manufacturing, the robotics of things are going to come, I think, more and more. So that's the thing. And then the end of that is that January 10, 2020, the Chinese Center of Disease Control again put on the internet the sequence of the COVID coronavirus. And this really, that's what happened. Basically, the information went in the internet. This time there were 350 laboratories in the world able to download the sequence, make a synthetic gene, and then the synthetic genes were used on top to make fully synthetic vaccine, which was the RNA, Moderna, 66 days in clinical trials, or by the Oxford group to make a recombinant adenovirus, basically splice the synthetic gene into the virus, and through the viral vector, in 3 months they were in clinical trials, and others used the green arrow, the synthetic genes to engineer mammalian cells, insect cells, plant cells to produce the recombinant protein. And then the recombinant protein was used together with basically with adjuvants to make vaccines. So that's more or less the history of that. And so looking at the vaccines of the future, basically, I think this is the way I see it. On the left, you see basically the vaccine design. There's no way. It's already been completely revolutionized by the artificial intelligence. We cannot do without it. Manufacturing is not there yet, but clearly is more and more AI is entering into the manufacturing processes, stabilizing, making more efficient, more better performance. And clearly on the right is how do we use that for clinical trials? And it's clearly there's a lot of use on improving the way we do clinical trials, recruiting patients, doing things. How it's going to be used for, real world evidence to licensing vaccines is still yet not mature, but it's going to get there as well. So let me see. Not able to advance. Okay. So what are the challenges for the vaccines of the future? Obviously, we have a lot of technology, but there are things starting from the top. We don't know durability. In the case of COVID, the durability has been a problem. CD8 T cells, we don't know how to use them. Mucosal and tissue immunity is something that is highly relevant. We don't know how to do it. Developing vaccines in 100 days is not yet there, and regulatory challenges are there. But these are the things in R&D which are high priority right now. I think, can you help me to advance the things because it's not advancing them? Okay, so let's look at the future a little bit. Which are the challenges? Next slide. Sure. Okay. Well, the next slide is basically a slide that I borrowed from Tony Fauci. Basically shows all the bacteria, viruses, and parasites were challenging and as potential emerging or re-emerging infections, which is facilitated by climate change, 8 billion people, deforestation, urbanization, travel, basically. So challenges are enormous. How do we prepare? And the main body now globally able to prepare is basically CEPI, which is globally supported by G7, G20, NIH, WHO. Hopefully, it's part of the negotiation of the pandemic treaty. And the main goal of CEPI is the 100 days mission, and basically, we made the prioritization of the virus families that may cause pandemics, and basically for each of them, for each family would like to have a prototype, and basically make a library of prototypes, and then basically make a sample of vaccines and produce all these in 100 days. That's the mission of CEPI is not very different from the mission of the NIH. Will also make a prioritization on the left of the families of viruses. And basically, they issued now 7 different grants of approximately 50 million each to make prototype vaccines for all this. So these are the CEPI and the NIH. Pretty happy to share with you the information that Europe is getting together with an initiative called European Vaccine Hub. And basically, this one is a 100 million grant, basically to set up a delocalized vaccine hub. And this we were informed last Friday that we basically have been allocated this grant. And the scope of this grant is basically to go from discovery to preclinical to clinical to manufacturing. And basically, to do 2 things. In yellow, see vaccine platforms. So you need platforms to make vaccines. And in blue, you see at the same time, you need to make products which are antibodies, monoclonal antibodies, and vaccines. At the bottom of each of the columns, you see the arrows that go up and down. That basically, this hub is willing to be connected with European vaccine manufacturers, European biotechs, academia projects, with everywhere. And basically, because projects can come in and out at any stage from any of these systems. So it's going to be a system very open for collaboration with anybody. And it's my pleasure to say that the Institut Pasteur in Paris is part of this European Vaccine Hub, and the Pasteur Network is part of it as well. So I think it's a first form of collaboration that is coming up. Personally, in Italy, I've been 2 years ago. I've been elected to the scientific director of a new institute called Biotecnopolo, which is basically part of this European Vaccine Hub now. And this basically goes from the identification to preclinical phase 1, phase 2, up to proof of concept of pandemic preparedness things. And obviously, it's not going to do the manufacturing, which has to be done in partnerships. What we do is basically what I call reverse vaccinology 2.0. Usually we start from blood from patients or vaccinated people, where you isolate monoclonal antibodies. And once we have monoclonal antibodies on the right, then you have 2 things. Once you have already immediately products that you can use for prevention and therapy, but at the same time, the monoclonal antibodies will identify the key antigens and the key epitopes which are necessary to make a vaccine. So I think starting from good protective monoclonal antibodies is the best way to get good vaccines. And so far we've been talking about viruses, but this morning I heard I was very happy, something about antimicrobial resistance. So our institute is the only one when we talk about pandemic preparedness. I say, well, we're going to do viruses, but we're also going to do bacteria. And so basically, that I promoted this also during the G7, which was done by Italy last summer. And basically, antimicrobial resistance will be a priority for my for the biotechnology, for the pandemic preparedness, because I consider the antimicrobial resistance a pandemic that is already going on, and we need to take care of it. So we're going to do bacteria and viruses, and hopefully we'll all together in a global collaboration we can do better. And with that, I would like to thank you for the invitation and for listening to my talk.
Thank you, Dr. Rappioli. Congratulations on your recently received grant, and thank you for showcasing the power of reverse vaccinology in global health, revolutionizing vaccine development, and how after 50 years of failure, innovations and breakthroughs can come from anyone. I think it's a nice lesson for all of us that persistence and experience are valuable, but so is the willingness to remain open to new perspectives, even that of a 5-year-old grandchild. I would now like to move on to our next keynote speaker, Dr. Carlo Costantini, who is a prominent researcher at the French Institute of Research and Development. He specializes in medical entomology and evolutionary biology, focusing on mosquito vectors of human diseases, particularly malaria. His work explores mosquito ecology, population genetics, and vector-host interactions, contributing to strategies for vector control. Dr. Costantini has conducted extensive fieldwork in Africa, collaborating on studies to understand the dynamics of Anopheles mosquito populations. He has authored numerous peer-reviewed publications that enhance knowledge of vector biology and disease transmission. His expertise supports innovative approaches to malaria control, including the use of genetic tools. Dr. Costantini is a key figure in international research networks tackling vector-borne diseases and actively mentors young scientists and promotes capacity building in endemic regions. Please help me welcome Dr. Carlos Costantini.
Okay, is there a pointer?
Yeah.
Okay. Well, thank you very much for that very nice introduction. I just have to add, sorry, that I am working a research unit that is called MIVEGEC and is associated with the University of Montpellier. And this acronym basically means that we work on the ecology, genetics, evolution, control of infectious diseases and vectors. So we switch, I think, a little bit subject here. So we're going to talk about insects and mosquitoes in particular. And I am basically at heart a zoologist. And I have the honor, by the way, to be hosted at the Department of Medical Zoology at the Institut Pasteur here in Dakar. So I work closely with colleagues here. And one of the questions that laymen and journalists love to ask to zoologists is something like, which is the most dangerous animal in the world? And you may be forgiven to think that charismatic large mammals like lions or leopards or even crocodiles are the most dangerous animals. In fact, if you look at the raw figures, and here you have the number of deaths, of human deaths per year per each one of these organisms, you can quickly see that the most dangerous animal in the world is actually mosquitoes as vectors of malaria and several arboviroses. Let's get a little bit more some context on these figures. So I've plotted here the cumulative number of malaria cases. You have that on the left. In the last 20 years or so, 22 years to be precise, and these are the official WHO figures. So if you look at that, by 2022 we have almost 7 billion malaria cases in the world. That means that roughly, on average, 3 out of 4 of humans in the world have been victims of a malaria attack on average. And I can well testify that because I've been among one of them. On the right, you have the cumulative number of malaria deaths. And in the last 20 years, we reach the appalling figure of almost 18 million, which is basically the equivalent death toll of World War I. As far as arboviroses are concerned, well, for malaria, the real burden is in Africa, in sub-Saharan Africa, where 90% of the burden
is. Whereas for arboviruses like chikungunya, dengue, yellow fever, or Zika, this is more of a global planetary problem, because even countries in temperate regions are affected by this problem, or are starting to be affected. And concerning number of cases, as of October 2024, the WHO figures for dengue, for example, is about 13 million cases in the world and about 10,000 deaths. So these are really serious health problems, mosquito-borne diseases. Now, after having looked at these shocking figures, so what can we do about this? Well, historically, the response has been to use toxic substances, so insecticides. And at the very beginning, and the early days, the larvae, the aquatic stages of mosquitoes were the target. And this was, as you can well imagine, and as you can see from these pictures, very demanding in terms of logistics, in terms of how expensive and or even difficult to do on such a large scale. But some good news was that in the 50s, when mathematical epidemiologists like George MacDonald started to do mathematical models about the transmission of mosquito-borne diseases, he also basically identified that it is not very efficient to try to target the larvae. We don't need to decrease the densities of mosquitoes. We really have to focus on the mosquito survival, because this is the most sensitive parameter in this formula, that is the formula of bacterial capacity. Bacterial capacity is just a measure of how fast the pathogens transmitted by mosquitoes can reproduce. Is the note of epidemiologists. So this led to a substantial shift in control strategies worldwide, and so still using insecticides, of course. The shift was to target the adults, not the larvae anymore, and to spray inside human structures insecticides that were long-lasting, so that have a very long residual effect, and with the premise that the mosquitoes were basically entering into houses to bite the people inside them, and then they would, after biting, rest on the treated surfaces and then killed by the insecticide. And at the end of the last millennium, so in the 1990s, there was a kind of a small revolution in the medical entomology world, because it was realized that an even more efficient way to reduce the bacterial capacity of mosquitoes was to target the insecticide not anymore on the walls or on the ceilings of houses, but rather on mosquito nets. And this is a very low-grade technology, but very efficient, because basically the people under the net are attracting the mosquitoes, and so basically they are kind of attracting them to pick the insecticide on the net. And so it is very efficient also in terms of economic gains, because you reduce the surfaces to treat, and at the same time the pyrethroid insecticides that are used on the nets, which are particularly safe for humans, have also an irritant effect. So there is also an additional protective effect for the people under the nets. So with this low-grade technology, we have achieved spectacular results. Beginning in 2005, there's been a mass deployment of these mosquito nets all across Africa, and in almost 10 years, there's been a reduction by about 50% of the Plasmodium falciparum parasite rates in the populations. And we can say that ITNs have contributed for most of this reduction. It has been even quantified to about 68% of this decline. And again, with this very simple technology, the Plasmodium falciparum case incidence has declined by 40%, and it has been estimated about 700 billion cases have been averted by malaria control with these mosquito control interventions. But in 2015, something kind of strange happened, and basically the pace of decline has started to slow down. And we are now, 10 years later or so, about 52% off track for malaria morbidity and 50% off track for malaria mortality compared to the 2025 GTS WHO milestone that was calculated at the outset as something to achieve by then. Dengue control in Africa is a little bit more complex. In a sense, dengue in Africa, even if it's been arbovirosis that has been circulating since a long time, has really emerged recently. And we don't have very many tools to address dengue as a public health problem, apart from enhancing diagnosis and case management and trying to prevent transmission with community action, or perhaps, but we have probably to address what is the efficacy of these treatments, spatial treatments, fogging or indoor residual spraying. So the fight is not over. We have still a lot to do to combat mosquito-borne diseases. And what are the causes of this? Well, the first culprit has been is cited most often is insecticide resistance. Malaria-transmitting anopheles are now increasingly resistant to all classes of insecticides, but particularly those that are used on to treat mosquito nets. And as you can see from the map on the right, in about 10 years from the mass deployment of ITNs, now there is very widespread resistance, so that deltametrin, which is the parameter that is used on nets, doesn't kill Anopheles mosquitoes anymore in many places. But physiological resistance is not the only culprit. We have all other kinds of resistance, like behavioral resistance. What is behavioral resistance? Well, as you can imagine, Anopheles mosquitoes to transmit malaria have to come inside the house and bite people sleeping inside the house. And now it has the more and more common to have mosquitoes biting out of doors where they are not exposed to the insecticides that are in the peridomestic environment. And another kind of behavioral resistance that we have pinpointed very recently in Central African Republic is that Anopheles mosquitoes have always been considered as nocturnal feeders. And we have realized that now they are avoiding exposure to insecticides also by biting during daylight when people are not sleeping under nets. In addition, of course, to the biting during the normal nocturnal window of time. And another threat comes from biological invasions and emergence of new vector species. So a new vector species coming from Asia has now invaded Africa. The vector is Anopheles stevensi. This is quite a dangerous vector in a sense. First of all, because it is adapted to urban environments where basically people at risk are a lot. And it's also very resistant to all classes of insecticides. And moreover, it's also very difficult to control because of its behavior. It has a lower propensity to bite and rest inside houses, so it's more difficult to control it by using conventional indoor-based interventions. Now, all this is happening in the context of global environmental changes, and we don't know precisely how this is going to affect the epidemiology of mosquito-borne diseases. Well, of course, everyone knows about climate change, although we don't know precisely what's going to happen. There are a lot of models out there, but some of them give even contrasting results, and some of the predictions are probably have to be applied more locally than globally. And other global changes may have a more significant impact, like, for example, urbanization. By 2030, about half of the human population in the world will live in urban areas, and Africa is, of course, part of this trend. Other environmental changes that can make a difference in the future is, of course, deforestation, or the management of water. I mean, mosquito-borne diseases are associated with water because of the aquatic stages of malaria. So agricultural practices are going to affect, of course, mosquito-borne diseases in the future, as they have been in the past. And the use of pollutants, we've talked about the insecticides, but we also have to consider, for example, fertilizers, microplastics. We are starting to study how this is going to affect, for example, the transmission and the competence of mosquitoes, or things like heavy metals, or even pharmaceuticals that are released as pollutants in surface water. We have to address these challenges for the future. And all this is, of course, happening in a context of globalization and increased exchange of goods and people, and this favors the exchange of pathogens and of vectors, as we already have seen an example with Anopheles stevensii. I'd like to make a brief detour to talk about a particular and understudied global change that may affect the biting behavior of dengue mosquito vectors that are diurnal mosquitoes, and this is artificial lights at night. So we have now preliminary evidence from Burkina Faso and from studies that we are carrying out here in Dakar that the light pollution at night might affect the biting behavior of the mosquitoes, and so this is going to increase the window for transmission for Aedes transmitted pathogens. So, what is going the future look like? After having probably been a little bit pessimistic, let's put some hope in my talk. On the one hand, we have to recognize that we are going to have the more and more powerful tools with which we can characterize organisms and environments, like from satellites to genomes. And at the same time, all these tools and new technologies are going to generate a lot of data, big data, and we need to have the tools to handle this data, analyze this data, and interpret this data, and artificial intelligence is already starting to help us in this endeavor. So, mosquito-borne diseases has already entered the genomic age, of course. This is since decades now, and what we have to expect is that mosquito control and mosquito-borne disease control is going to abandon the use of insecticide, or use insecticide less and less as always a complementary measure, and we have to enter a new way to control these diseases, like exploiting genetic technologies. There are two possible approaches for that. We have either population replacement or mosquito population suppression. With population replacement, we are basically trying to heal the mosquitoes, or rather to make pathogen competent mosquitoes into pathogen incompetent mosquitoes. And with population suppression, we are trying to basically eliminate with different genetic technologies, sterilizing technologies, to reach a point at which mosquito populations no longer exist, at least at the local level. So there are different technologies. All this may seem a little bit science fiction, but you have to consider that this is something already happening right now. For example, this Oxford-based biotech company, Oxitec, is already releasing OGM mosquitoes in Djibouti to suppress Anopheles stephensii there. So there are different techniques. I'm going to talk about 3 of them. The first one is the sterile insect technique. The sterile insect technique is basically sterilizing male mosquitoes with ionizing radiation, and then releasing large quantities of these males in nature so that they can mate with females. And if they are successful, the mated females, because they only mate once in their life, lay infertile eggs. And so this is contribute to the decline of the population. One of the main problems with this technique is that you need a mass breeding facility to produce extremely large number of males, and you have to sex them. So you have to separate the males from the females in a very precise way, because you don't want to release the females, of course. Another technique, which is a transgenic technique, is this Oxitec-friendly mosquitoes technique. And basically, this is a dominant lethal gene that is conditionally expressed in the absence of an antibiotic, tetracycline. So this allows to produce large quantities of transgenic males and females in centralized facilities where they are reared with tetracycline. And then you basically release these males. They mate with the wild-type females, and the wild-type females, they produce non-viable female offspring. So only the male offspring survives, and this basically contributes to the spread of the gene, of the target gene in nature, and this eliminates the need for large-scale mosquito production facilities. But of course, one has to be attentive about GMO requirements, and so. And another way to fight against mosquitoes genetically is with Wolbachia infected mosquitoes. This is at the same time can be a population suppression or a population replacement technique. Wolbachia are obligate intracellular bacteria, symbiotic bacteria, that have found a way to manipulate the reproductive system of insects in general, because they are not only in mosquitoes, but in many other insect species. And when uninfected females mate with infected males, these have reduced fertility. So this technique basically leads to population suppression. Whereas when infected females mate with infected or uninfected males, they spread the Wolbachia into the population, and so this contributes to population replacement. And the good news is that the Wolbachia infected females are much less competent for several arboviruses. So this can be used as a way to have incompetent Aedes mosquitoes in the field. Now, when you do all these controlling interventions, you also need some ways to monitor the populations that you are trying to control. And even in this field, we are going to see very new advancements thanks to new kinds of sensors combined with artificial intelligence. And so we will have new devices that will allow us to detect, to count, to identify, and to classify mosquitoes automatically. And so this will give us a more powerful and high throughput approach to surveillance, even using, for example, citizen science. Another area where we're going to see very important advances is in the use of environmental DNA. And this can be used at the same time to monitor the presence of pathogens in mosquito tissues that are collected non-invasively, but they can be used also to study how mosquitoes interact with their environment, for example, by looking at the pollen of that can stick to the body of mosquitoes, so that we can understand where do the mosquitoes feed, on which plants, for example. But more generally, we can use it to monitor mosquito populations, to detect their occurrence, or even perhaps one day to monitor their density. Now, all this is also happening, and we can many people think that we know almost everything about these vectorial systems now. And in fact, this is probably not true. The genomic revolution is basically producing good surprises. I just cited here an example. We've been basically discovering, for example, a new malaria vector species that is only present here in Senegal, in neighboring countries. And this has been possible only because we have studied thousands of whole genomes of these mosquito populations from the field. So, as a last message, we need to be creative. Sky's the limit. And this is just a very perhaps amusing example of the research work of one of my PhD students that is studying the effects of coughing on mosquito aging. And so he's found that with high doses of caffeine, we can basically increase the pace at which mosquitoes senesce. And this, of course, can have very important consequences on vectorial capacity. So perhaps one day coffee will be against dengue. And I'd like to conclude this talk because this is the Pasteur Centenary with a very old photograph that was taken about 30 years ago at the Institut Pasteur in Dakar. And some of you may recognize some of the guys in the image. And these guys have now become, many of these guys have become heads of departments or scientists well recognized in the at an international level and experts in their own field. So we really have to make really have to carry on investing in human resources. We really have to invest in human brains. Artificial intelligence is good, but we also need biological intelligence. Thank you very much. Question?
Yes.
Okay.
Thank you, Dr. Costantini. Does anyone have any questions for him? Or would you like to play a game of guessing who was in the picture? I guess you're free. Yes. You've got one question. The mic.
Okay, thank you very much, Dr. Constantini. It was a really interesting talk. Just a quick one on the friendly mosquitoes. So I may have missed that one, but how do you know the fitness of this type of mosquitoes regarding the wild type one? Are you comfortable that those ones are able to compete with natural mosquitoes in nature in order to be able to 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 fight them or to compete them in real natural conditions? Thank you.
Okay, thank you for your question, and you hit the nail. I mean, this is part of my job. In fact, my part of my raison d'être of being a mosquito ecologist in the first place. So yes, I mean the Oxidec company has, of course, tested the fitness of the mosquitoes in laboratory conditions, but to be true, we don't have any idea what's the fitness in the field. So this is something that should be addressed. And when I realized that this operation was happening, it has started a few months ago, I was a little bit surprised because, to my knowledge, there's no published data about fitness of these mosquitoes in the field. Okay, this is an interesting story because it's a very long story, so I have to make it really short. But basically, the most important malaria vector in Africa belongs to a complex of sibling species. So basically, you cannot distinguish them morphologically. And in the 50s, they were still considered as only one species. But when they were basically there were mass control campaign with DDT at the time, and so they were very successful in some places, very unsuccessful in other places, and that led to the discovery that basically the good vectors were indeed killed by the insecticides, but the non-vector, which couldn't be distinguished morphologically, were not touched by the insecticide because they didn't go inside houses. And it is a little bit of a similar story here, although this vector species is a hybrid between two different species, basically. So, and usually hybridization has always been considered like cul-de-sac from an evolutionary point of view. And in these cases, hybridization has led to some recombination of biological traits that have made these vector species a little bit different from their parental species. So we are just starting to study now a little bit about the bionomics, and we already know, for example, that it is much more susceptible to insecticides. So this is kind of surprising, and it's also much less anthropophilic. So it bites humans to a lesser degree than the parental species. So it's kind of a worse malaria vector in a way. But it's very interesting because its geographical distribution is mostly in the mangrove area in the coast of Senegambia. And it's quite interesting because this is where malaria control interventions have been very efficient. So you don't have much transmission left here, whereas the core in the eastern part of Senegal, for example, you still have a lot of malaria transmission. And so this may be the explanation. It's just because there are two different vectors.
We have a last question from Hadi Chigo, who's from the Epidemiology and Data Science Division at IPD.
Hello, Dr. Constantini. Thank you for the insightful talk. I was wondering if you had any potential insights on the ecological consequences of these population suppression techniques. Thank you.
For the mosquitoes, you mean? Or from ecosystem level?
Well, for, let's say, the ecosystem level? Thank
Okay.
you.
Again, we don't have much knowledge about this. On one hand, we know that mosquitoes are, of course, part of the food web. So mosquito larvae are fed upon by a lot of organisms and mosquito adults as well. And we also know that mosquitoes, for example, contribute to some extent to pollination by feeding on flowers. So there may be some ecosystem services that mosquitoes are providing, and we don't know much about it. So we're just starting now to address these questions. We always see mosquitoes as our enemies. To some extent, they may be our allies, because as an ecologist, I always used to say the worst enemy of our mosquitoes is another mosquito. Thank you.
Thank you, everyone, for staying to this last final bit, which is our final panel discussion. In this panel discussion, we will talk about empowering the communities, shaping prevention and policy for future pandemics. This panel will be moderated by Dr. Rebecca Grace, who I'm inviting now. I will introduce each of the panelists, who will be Professor Heidi Larsen, Dr. Karel Pele, Dr. Boubacar Diallo, and Dr. Bambagay. I would like to start by giving a brief bio sketch of Rebecca Grace, who is the Executive Director of the Pasteur Network. She previously served as Director of Research at Epicenter, an epidemiology and research branch of Médecins Sans Frontières. Her work primarily focuses on the prevention of infectious diseases and emergent infections in low and middle income countries, with an emphasis on public health intervention studies and efficacy trials of new vaccines and therapeutics. She also prioritizes professional development, mentoring, and management training for underrepresented populations in scientific research to foster career advancement and healthcare innovation. Dr. Grace holds a doctorate, 2 master's degrees, and a bachelor's degree from Johns Hopkins University, as well as a habilitation à diriger des recherches from the Faculté de Médecine Paris-Saclay, France. She has authored over 200 peer-reviewed publications and participates in numerous scientific, funding, and international organization committees and advisory groups, particularly in vaccine development and epidemiological studies among vulnerable populations. Additionally, she is a member of the Strategic Advisory Group of Experts at the WHO. Please give a round of applause for Dr. Grace. Yeah, that's all you. Yeah, go on.
We invite the panelists up?
Yes, sure. So next I would like to invite Professor Heidi Larsen, who is founder and director of the Vaccine Confidence Project and professor of anthropology, risk and decision science at London School of Hygiene and Tropical Medicine. She is also clinical professor, Institute of Health Metrics and Evaluation, University of Washington, guest professor at the University of Antwerp, and a Chatham House Center on Global Health Security Fellow. Professor Larsen previously headed global immunization communication at UNICEF. She has chaired Gavi's advocacy task force and served on the WHO SAGE working group on vaccine hesitancy. She is author of Stuck: How Vaccine Rumors Start and Why They Don't Go Away. In 2021, she was awarded the Edinburgh Medal, and the BBC named her as one of the 100 most influential women in the world. Professor Larsen's research focuses on the analysis of social and political factors that can affect uptake of health interventions and influence policies. Her particular interest is on risk and rumor management, from clinical trials to delivery, and on building public trust and public cooperation during emergencies such as disease outbreaks, natural disasters, terrorism, and conflict. Please give a round of applause to Professor Larsen. I would now like to call on Dr. Boubacar Jallo to come on stage. Dr. Jallo is the program leader of the Epidemic Intelligence and Outbreak Response Unit at Institut Pasteur de Dakar, IPD, and the coordinator of the extension of the Syndromic Sentinel surveillance in West Africa. He is a trained medical doctor with postgraduate training in project management, epidemiology, and control of infectious diseases from the London School of Hygiene and Tropical Medicine. He has previously served the World Health Organization Regional Office in Africa as Incident Manager during the West African Ebola outbreak in Guinea, pulmonary plague outbreak response in Madagascar, and the 9th and 10th Ebola outbreak responses in the Democratic Republic of Congo. He has worked also with the CDC Atlanta on polio eradication in Guinea, MSF Canada on malnutrition in Niger, the Canadian International Development Agency in Abuja, and the Carter Center on guinea worm eradication in Mali. Please give a round of applause to Dr. Jallo. I would like to call on Dr. Karel G. Pele, who is the head of Health Systems Strengthening Unit in the Department of Public Health at Institut Pasteur de Dakar. Dr. Pele holds a PhD in Biological Sciences in Public Health from the Harvard T.H. Chan School of Public Health. She is a public health specialist with over many years of experience working internationally with NGOs, research institutions, and ministries of health. Her work focuses on developing and testing innovative strategies to enhance equitable access, quality, and acceptance of diagnostic and vaccination services using digital tools and strengthening epidemic preparedness at community level in sub-Saharan Africa. Prior to the Institut Pasteur de Dakar, Dr. Pele was senior scientist, public health at FIND, Geneva, and infectious disease program manager at the Broad Institute of MIT and Harvard in Boston. Please give a round of applause to Dr. Pele. And last but not least, Dr. Bamba Gay, who is an associate professor of biomedical informatics at the Emory School of Medicine in Atlanta, Georgia. He trained in biology and specialized in pharmacology and bioinformatics, and is a medical doctor from the University of Sheikh Anta Diop in Dakar. Dr. Gay's research focuses on preventive cardiology, from primordial prevention to precision medicine, emphasizing the role of genomics, biomarkers, and artificial intelligence in transforming cardiovascular epidemiology. In 2018, he co-founded a global network of methodologists, epidemiologists, clinicians, and researchers, particularly from sub-Saharan Africa. Dr. Gay plays a central role in the Alliance for Medical Research in Africa. He is dedicated to strengthening research capacity, fostering innovation, and ensuring that health research in Africa addresses the continent's unique challenges and needs. Thank you for being our panelists, and we look forward to a very enriching chat. Thank you.
So this afternoon's session focuses on communities, and it's something which is often forgotten a little bit by scientists who sometimes forget that there's something outside of the lab, and that's the people. And we'll talk more about that the rest of the time here. And so we have the great pleasure today to hear from our four panelists. And what we'll do is we'll just go around from Heidi all the way down to Mamba. And so we'll start with Heidi, and I believe Heidi has a video to show as well, who will kick off our conversation.
Okay, slide. Okay, great. Do I do this? Just want to go to the next one. Okay, perfect. Okay. I'm just going to show you, we're starting with me because I'm going to do the problem setting and then we're going to have the solutions.
hopefully. I thought I would start with the bigger picture. I was lucky enough to get a MacArthur Award a couple of years ago, and that led me to having the ability to do a global study, 70 countries, on people's experience during COVID around the world. Societal experiences, a multiple range of things. But we were also trying to understand, who did people trust, who did people turn to? And I just put a subset of the different trust ecosystem to look at today, because when we think about community, oftentimes we're very linear. We think about one, let's look at community, or let's look at scientists, or let's look at something else. But I think we have to look at it in perspective. And in the countries that were included in the broader 70 country study, I pulled up trust in science. The question was, in the event of another major crisis, who would you trust to act in your best interest? And also, there was another part of the question was also for information. Globally, you can see the numbers. The reality is, and I ranked this based on people's trust in scientists, which sadly, the green is when it was the highest trust. The bluish one is the second level. So Ghana, interestingly, was the only country that had scientists as the most trusted among the different options here. Unfortunately, I was surprised. Senegal had the lowest reference to trust when you have some of the best scientists in the continent. So we got some work to do, Amadou, or your broader team, and we're here and ready for you. Anyway, this gives context. And then the yellow, I just highlighted community leaders. Now, overall, Africa had considerably higher trust and turning to community leaders than the global average, which was 55. But globally, there was quite a high deference to families and family doctors, much more so than scientists. After family and family doctors, particularly in Africa, were religious leaders. So also when we say community leaders, we have to think, because reality is religious leaders are part of the community, but we pulled that out because they have a particularly strong one. So in this context, when I did a lot of work with my team, we do a lot on trust building, on trust mapping. I founded the Vaccine Confidence Project to be monitoring specifically vaccine confidence and get a metric so we can track it over time and look at trends. But we had a big initiative. It was an EU grant with multiple partners to support trust building and community engagement around multiple Ebola vaccine trials. And when the phase 1 trials, there were 2 that were about to start in Ghana, Ghana was the country we were least worried about in terms of disruption societal. It turned out to have some of the worst disruptions. And I'm going to show you a short, we wrote an academic paper on it, but I sent one of my top researchers and a video maker to Ghana to go around and talk to all the different, the journalists, the religious leaders, the community leaders, the parliament, the FDA, the scientists. So you can see, and it's now used as a core curriculum in the University of Ghana, along with the academic paper, a problem approach, which you rarely learn in school. It's always a linear, do this, get this evidence, then you do the policy, and then you do the implementation. Well, let me show you what can happen, and some of you have experienced this. I'll turn to my trusted colleague to start the video. Needs a little sound.
The body count is rising. Stop. The scourge will be poor shoes, no signs of starving. The fear and mistrust of a violent turn in Nigeria's capital, Monrovia, an angry crowd, many of them armed with clubs, raided an Ebola isolation route in the city's largest slum. It's a process that usually takes years, but in a race to beat the Ebola epidemic, doctors and scientists are speeding up efforts to create a vaccine against the virus in a matter of months. Fight Ebola.
However, we've never had a trial as sensitive a virus as the Ebola virus.
Because, mind you, we're coming from a backdrop where Ebola had killed, between Sierra Leone, Liberia, and Guinea, had killed almost 11,000 people within that short space of time. So there was so much fear in the system.
It was meant to kill people. That was the news going around.
What were you going to use as the vaccine? Is it an Ebola vaccine or is it another vaccine? What is it? What is the component of the vaccine you're going to use?
People felt like this thing was being done undercover.
Why Ghana? Wouldn't it involve bringing a virus to Ghana before you start? Did you know the difference between a virus and a vaccine? Do we have the systems? Do we even know how to register trials? Have people been paid a bribe to undertake this trial? Are these scientists taking us for a ride? Where is our regulator? All these questions were asked.
So the whole society was up in arms.
It wasn't a case of the laboratories or the ability to go about the test. It had to do with the issue of fear.
The media broke it as, that's what we've discovered. Here is this news about some clandestine vaccine trial in the Volta region.
Once the FDA began dealing with the protocols and the checks and balances and having to speak to the center in Hohoi that was going to deal with it, it leaked, or it came out. It came out. Once it was Ebola, it became an issue.
I had a call from a person from the US. Then he said, there's going to be an Ebola vaccine trial in the Volta region of Ghana. There's a midwifery school there, and then some students have been selected for the trial.
We have not given approval yet. We have given conditional approval for preparation to start. And the preparation did not include the recruitment of subjects. And the main fear was one person gets, or there is a failure. Then it is something that will spread. That is a feeling of
TGIN needs to be highlighted in this trial. They were the first to issue a statement. I'm a victim of vaccine injury. I wanted the government to listen. I saw from Star FM Online, a local radio station, reporting that a midwifery school in the Volta region is about to go through this exercise. I realized that if we go a bit thick, nobody will listen. Ebola is no more just a disease, but a business. When I did the write-up, a strong group in the Volta region came out with a press release that they can't sit for the people to be used as guinea pigs. Actually, they just copy-paste some of the things that I wrote.
The political outfit of the ruling government, that's the NDC, in the Volta region, to issue the statement condemning it.
When we heard about the incentives, we heard about the trials. Like I said again, we also had a lot of information from our brothers and sisters who come from the region and stays elsewhere in the diaspora. So we made a press release. People were not educated enough. Leadership
for us in the region were not consulted carefully, if they were dying, we might have lost people who were going to vote for us anyway in the first place. And that was our agenda. Within 10 minutes, it was out there. We went to the social media, we went to radio, we went to print media. There was spontaneous response from Ghanaians.
And not use the youth in mapping up for demonstration. The future at this time for our country's development, we will not want to see social unrest due to negligence in educating the person.
About the 9th or 10th of June, there was a discussion on our national parliament that there were going to be trials in Ghana.
There was an initial allegation that the trial had already started in the Volta region without information to anybody. First, that was debunked. There were issues of bribery.
It is said that persons who volunteer for the exercise will be given 200 cedis and a mobile phone.
Mr. Speaker, MPs from the region have motivated the call for from panic-stricken constituents who believe that this trial is aimed at spreading the dreaded Ebola disease in the Volta region. Systems that have been put in place to enable such research to be conducted in this country are not good enough.
That's right. They have taken their consent. It is a met the minister on June 10th and raised 9 issues of consent.
The academy is not interested in making unnecessary waves. We saw a situation quietly, we resolve it, send a documentation to where it's needed to change or improve policy. That was what we thought we were doing.
GAS, their concerns were the same. They had petitioned the minister, they had petitioned some other members of government.
Concerns were not addressed about the safety issues and the surrogate markers of immunity, of efficacy to whatever vaccine that you are going to develop.
The anger of the members of parliament, the anger with the people from the Volta region was as a result of the fact that they felt they had a basis. And the basis was that it was scientists who were challenging the FDA.
Ghana Academy of Arts and Sciences has the best scientists in our country. They are the people that have written the pinnacle of their profession. And if they are on the same side of parliament, Mr. Speaker, we are a good topic.
At the time Parliament had its discussion on the 9th of June, a provisional approval had been given for one of the trials to start in the Volta region. On the floor of Parliament, there was a fear that no trial of any Ebola vaccine can take place in Ghana.
We shouldn't suspend it. It should be stopped. Not in Ghana here. It should be done somewhere else. If they want to do it in Ghana, they should do it in the laboratories with mice, rats, and chimpanzees, but not with human beings. We would urge the Minister for Health and all those responsible for admitting or permitting this trial to take place here to reconsider, not just to suspend it, but to say no, thank you.
The ministry has decided that the best thing to do is to suspend the trial. Tony Goodman admitted that the ministry failed to take the public through the necessary education, which would have eased their fears about the process.
To bring calm immediately to the situation, there was the immediate suspension of any further activity on it. Unfortunately, there were strict timelines that we had to meet, or that the company that was dealing with it had to meet. And by the time all that had been done through Parliament and through the checks and balances, the timelines had expired.
That's the country that trusted scientists the most. But one of the issues was that the scientists also were starting to question the process and the sensitization. So I'll end here and we'll have a discussion later. Thanks.
Heidi for showing us this video, which I also feel as though you could substitute Ghana for pretty much any other country in the world. And you could substitute Ebola for lots of other things as well. And it's an important lesson. And so today we have 3 panelists who are also going to talk about some potential solutions and some ways to move forward. And so we'll start with Karel, if you'd like to begin speaking.
All right. Thank you, everyone. Thank you, Heidi, for sharing this video, which highlights the issues around confidence for vaccine trials. What I'll be sharing with you today is more around the strategies that we have at Institut Pasteur to build community resilience. So we've all seen or felt the impact of the COVID-19 pandemic on our personal lives, on society, and on health systems. We've seen the disruptions to essential health services with the increase in the zero dose children who have not been vaccinated, reduced access to health services due to restrictions. We've also seen the impact of climate change, impact on flooding, on health structures, transmission of diseases. We also know that conflict can also affect the movement of populations, moving populations further away from health systems. So all of these are considered as force majeure that have devastating impact on our lives and on health systems. And so the question is, how do we mitigate the impact of these events on our health systems? We tend to talk about health systems that are resilient, talking about communities that are resilient, but I wanted to first dive into quickly what we mean by a health system. We use the term a lot, but I thought it might be good to refresh what we actually mean by a health system. So the WHO defines a health system as a system that consists of all organizations, people, and actions whose primary intent is to promote, restore, or maintain health. It is built on the framework of 6 building blocks: service delivery, so ensuring that we deliver quality services; a health workforce, one that is trained and productive; information systems, being able to generate and use data and knowledge; medical products, ensuring that vaccines, diagnostics, and treatments are available; financing, ensuring that we have fair and justifiable financing; and then strong leadership and governance. And so through interventions through all of these 6 building blocks, the aim is to really improve access and coverage of health services that are of good quality and that are safe, to improve the health outcomes of populations. And then building resilient health systems or strengthening health systems. When we say health system strengthening, we're actually talking about tools that allow all people to have access to quality health services without financial hardship. And that means really targeting populations that need health services the most, focus where the needs are the biggest in our health systems. And then this is based on a concept of equity, therefore based on the understanding of the determinants of health. What are the factors that are driving access or lack of access to health services? And so this health system strengthening strategy needs to be cross-cutting. It needs to tackle different health systems block, and it also needs to sustain impact long-term through policies and regulation, organizational structures, and driving behavior change, which is the third dimension of the health system cube. For those who took a health system class, they know this cube really well. So our health system strengthening strategy at IPD is really based on this concept of looking at issues from a health systems approach. We've built our health system strategy this year through consultative workshops with the Ministry of Health, academia, research institutions, community association, and civil society to really focus our strategy on the needs of the people of Senegal and also built on and leveraging on the strengths of IPD. What we envision is a unit that is an innovation hub and trusted source of evidence generation for strengthening public health systems in Africa based on 3 objectives. The first is to enhance acceptance and acceptability of innovative vaccination solutions for underserved population, improve the availability and accessibility of diagnostics for priority disease, and thirdly, to evaluate the impact of public health interventions. And all of this through strong community engagement and also through the generation of evidence that is then translated into actionable recommendations to decision makers here in Senegal. So I'd like to now share one of the initiatives that we have launched this year that is based on the first objective around acceptance of vaccination here in Senegal, and that I'd like to share some quick results with you just to give you a bit of a taste of what we found. So this initiative actually started from the observation that there's a degradation of trust across the world of public health interventions, notably vaccination interventions. And here in Senegal, we've seen this in our previous work with Professor Cheikh Ibrahim Agnong, where we've seen erosion of trust for the HPV vaccine across Senegal. Vaccination acceptance can be due to several factors. It could be due to misinformation, the spread of rumors, knowledge gaps, access issues, and also politics, personal beliefs of people or spread of politics through different media. So at Institut Pasteur, we're very interested in understanding what factors drive the decision to vaccinate across the life course. And we've taken this life course approach because vaccines don't target populations the same way. There may be different issues for different types of vaccine. In this research project, we're looking to assess the knowledge, attitudes, and perceptions of vaccination across the life course in Senegal to specifically monitor changes in response to targeted evidence-based health messaging campaigns in communities. And we're looking as proxy for childhood vaccines, the EPI program, adolescent vaccine, the HPV vaccine, and for adults, the COVID-19 vaccine. And we've used a mixed method approach to tackle this issue, looking at quantitative household surveys across the 14 regions of Senegal, which is wave 1, then going into deep dives through qualitative research, individual interviews and focus groups to really understand specifically the factors associated with high or low acceptance, and then developing targeted sensitization from the research results, communicating back to the Ministry of Health on what we found in terms of access issues, information gaps, rumors spreading in the populations for these 3 types of vaccines. Going back into the populations to assess if our interventions move the needle, and reverting back with some recommendations to the ministry. So the next couple of slides are just some preliminary results from our household surveys that are across 14 regions of Senegal, 3,600 households. What we see in 2024, which is our data points from this research, is that when we ask the respondents, do they think vaccines are important for children, safe, effective, compatible with their beliefs, or important for all populations? We're back at pre-pandemic levels, so similar levels from the 2016 percentages. And so this is actually really good news for Senegal, because there were a lot of questions around the impact of COVID-19 on different vaccination programs. Despite this strong confidence level that we observe in 2024, there are regional disparities. When we look at the 14 regions of Senegal and we look at the indicator for vaccine confidence for vaccines in general, we see that there are specific regions such as Kédougou, Ziguinchor, and Dakar where their vaccine confidence is below 80% compared to the rest of the country, indicating that there are specificities to each region that needs to be taken in account when we talk about vaccination and vaccination acceptance. We also see differences in terms of vaccine confidence across the life course. So here represented are percentages of the population responding to the survey that are either confident, hesitant, or in between. So for the EPI vaccine or the measles vaccine specifically, we see really strong confidence, 90% to 88%. And this is really not surprising for us here in Senegal. The EPI program has been around since the 1980s and has been a very successful program in Senegal. But when we go to the HPV vaccine that has been more recently introduced in Senegal and the COVID-19 vaccine, we see an increase in the hesitancy observed across these two vaccination groups, 15% compared to 25%. When we focus on a region like Dakar, which is a region of low vaccine confidence, and we try to ask questions around what are the information gaps, what are potential factors that are associated with low vaccine confidence. When we ask specific questions around the HPV vaccine, almost 3/4 of the population in Dakar responding to the survey were not aware of a vaccine that prevents cervical cancer. And that's a major issue. 72% were not aware. Compared to the Pink October campaign, that is a campaign for cancer affecting women, so breast cancer and cervical cancer, where a lot of people, 69 to 73%, are aware of this campaign. And lastly, when we deep dive again more into whether people think they have enough information to inform their decision to get vaccinated themselves for COVID-19 or their child for HPV, we also see again some big differences. In the EPI program, we see differences. Again, strong feeling of confidence for the EPI program, some degradation when we move to COVID-19 and HPV. And specifically, people specifically ask about information around the disease that are prevented by the vaccine, information about the national recommendations, and the age to start vaccination or about the disease itself. So this is just a few slides just to give you an idea of what we're conducting here at Institut Pasteur, really using research to inform to generate results that can then inform communication campaigns, inform issues around access of vaccination services in Senegal, so that the intervention that are proposed by the ministry are targeting specific issues. And so the long-term goal for Institut Pasteur is to establish these observatories across the country where we can really monitor changes in vaccination confidence and changes after the introduction of different strategies. The last slide that I want to show that I'm not going to cover today is the second initiative that we are covering in our unit, which is community-based surveillance. It's another strategy that we have in place to improve resilience in communities here in Senegal, where we are establishing the extension of the forest system that Dr. Diallo will talk about shortly, to include a community approach where community health workers and members of the community themselves can really take ownership of their environment and contribute to protecting the health of their themselves and their neighbors. So with that said, I'd like to thank you for your attention and thank our partners that are with us in this project. Thank you very much.
Thank you, Carol. That was the first response to Heidi's video from Ghana, which could easily have been anywhere else in the world. Our next presenter, Dr. Diallo, would you please come up? We'll go into a little bit more detail about the 4S surveillance system and community involvement. Then after he speaks, he'll be followed by Dr. Bamba, and then we'll discuss a little bit more, and of course with all of you.
Thank you very much. Good afternoon, everyone. So it's a pleasure for me today to present one of the best surveillance system that has been put in place by IPD in Senegal as well as outside of Senegal. Okay. So I'm going to share that strategy, as I said, which is called the syndromic surveillance system of Senegal, but also called the 4S network, which focus more on malaria, respiratory viruses, arboviruses, as well as viral hemorrhagic fevers. So what are the main objectives of this strategy? So the first one is to identify and early detect the occurrence of health events. The second one is to monitor and predict trends of diseases that are under surveillance. And the third objective is to strengthen national capacities to detect, report, and respond to unusual events in line with the international health regulation. And the last one is to develop partnerships. So look at the evolution of that strategy. It started in Senegal in 1996 by setting up influenza virological surveillance in Dakar. So we came up with some sites in Dakar by doing influenza surveillance. Later on in 2011, we strengthened that surveillance system by integrating the epidemiological surveillance data for ILI, which is the influenza-like illness. 1 year later, we also tried to strengthen the same surveillance system by adding other febrile syndromes like malaria, arboviruses, and diarrhea. But also, plus influenza, we added other respiratory viruses like RSV, adenovirus, corona, and enteroviruses. And then from that year, we started the extension outside of Dakar region, but going to other Senegalese regions. And then in 2015, so we started implementing the SARI surveillance in hospitals. And then from 2017 to 2022, plus the same system, we are working on it, and then we integrated the One Health approach, but also the MR surveillance, but also, adding viral hemorrhagic fevers. Looking at today, we cover 38 sites in Senegal. Among those, we have 31 community sites and 7 that are hospital sites. So we have at least 1 site in every single region. And we also have 3 One Health sites. As you can see, the health districts that are colored in like a pink color are the health districts that are hosting syndromic sentinel sites. But the fact that this strategy is making a very huge impact in the health system in Senegal, we have been pushed by the MOH to extend that strategy in the entire health districts of the country. So they want the entire health district to have at least 1 syndromic sentinel site. So it has a steering committee. When that steering committee is composed of the MOH, WHO, CDC Atlanta, as well as IPD. So the steering committee meets once every 3 months, but we also have the national coordination meeting, which is held once a year. So these are the case definitions, as you can see. So as we monitor, the first part to be integrated in the system is to have a fever. So we use the WHO case definition, but we also refer to the same one when it comes to malaria, arboviruses as well as respiratory viruses. So I think the data collection tool, which is called the Teranga mobile collector. So this is the application that goes with the strategy. So it will help us to collect data from the healthcare level up to the laboratory. So we can see there is also the interoperability between that platform and the DHS ESS2. So that will make things very easier for us. So that's why we have been extending the same application in some West African countries. So we do the One Health approach. As you can see, in some sentinel sites, we try to monitor to see how outbreak can start. So we do monitor animal health plus those syndromic sentinel surveillance we have. We also monitor vectors as well as wastewater and watering places. We have teams that will go every month to collect samples and to be tested in IPD labs. But we also do environmental surveillance by installing some weather sensors in some of those sentinel sites by monitoring rainfalls, wind speed, air quality, and humidity, as well as temperature. So as you can see, we sample blood and nasal swabs from pigs, but we also monitor live bird markets in those One Health sites. So here you can see some of the results from 2015 up to now. Dozens of outbreaks have been detected through those sentinel sites. We are detecting all of type of arboviruses, those pathogens that are circulating in the country. So you can see West Nile, Rift Valley fever, dengue serotype 1, 2, and 3. Even we can see in Dakar on the bottom part, you can see we detected dengue serotype 1, 2, and 3, chikungunya, West Nile, and so on. But also you can see the Crimean Congo hemorrhagic fevers as well that have been detected. I will give more detail on this one later on. So you can see those pathogens distribution in the country. So you can see almost all the regions are really reporting dengue cases. So this is the result for 2 years, 2022 and 2023. So we had 20 Crimean Congo outbreaks in Senegal. Why am I saying outbreaks? We can also 20 cases, but every single case was an outbreak detected in the country. So we can see on the green node, the health districts that are hosting a sentinel site are color in the pink color, and the white health districts are districts that have not have syndromic sentinel sites during those specific periods. But you can see how powerful are the syndromic sentinel surveillance. Wherever we detected Crimean Congo cases, there are color in green. They were detected at the very early stage. None of those cases have presented a complication, but you can see they are located in the white districts because there is no surveillance system. And if you can look at the deaths occur from those health districts that have not the syndromic sentinel surveillance during that specific period. All the cases detected in the syndromic sentinel surveillance sites were detected at the early stage, and none of them have died. So now I'm going to talk the extension of that strategy. At the end of 2022, IPD was approached by Africa CDC and WAB. The fact that this strategy is working very well in Senegal, they supposed to expand the strategy in some neighboring countries. So that's why Gambia and Mauritania were supported by Africa CDC and WAB. And after that, Bill and Melinda Gates Foundation and supporting the setting up of the system in Cabo Verde, Mali, Niger, and Guinea-Conakry, and later on this year, we are joined by the Global Fund supporting 5 more countries, which are Togo, Guinea-Bissau, Liberia, Sierra Leone, and Benin. So you can see on the map, countries that are colored in green are the countries where we set up the system in 2023. The yellow colors are countries where we are installing the symbolic sentinel surveillance site this year, and next year are the countries that are colored in green. But for now, we have funds for Liberia, Sierra Leone, and Benin. So you can see the distribution of those sentinel sites in West Africa. So in Cabo Verde, you can see by at the middle of the left side, we are on 2 islands, the Santiago Island, which is the capital city, and also the Santa Maria Island, which is called Island of Sal. So now, before wrapping up, what impact IPD has been made so far on the continent based on that surveillance system we put in place? As I said, we started in the Gambia. So when we got the Gambia beginning of 2023, during the first assessment we did with the country to come up with the 2 syndromic sites, the first one was to set up one in the capital city, which is called the Brikama Hospital, and the second one was like 3 kilometers far away from the capital city, which is called the Bansang Hospital. So please look at the results. When we set up this system beginning of 2023, 8 months later, we got a phone call. So what we did, we trained the healthcare workers from the sentinel sites to enable them to detect pathogens when they come to those healthcare facilities. And we also put the sample shipment system in place within the country to quickly ship all the samples that will be collected from those sentinel sites to the National Public Health Lab to be tested very quickly. So we set up all the system. So now, and also with the team, we will be working with the National Public Health Lab to strengthen their capacity so that they can be able to detect all of those arboviruses pathogens as well as viral hemorrhagic fevers. 8 months later, as you can see, in September 2023, the Gambia detected for the first time in the history a chikungunya case, which is like the arbovirus. So we worked with the team. In 24 hours, they were able, as IPD, as the reference lab for arboviruses. When they confirm first, they have to ship the sample to Dakar so that IPD can confirm. So that was done. And this case was confirmed. We did the sequencing, we published the article, and we gave the authorship to the Gambian team. Now, 1 year later, which is like 3 months ago, for the first time again in the history of the Gambia, the same syndromic sentinel sites, they detected the first yellow fever case. In 48 hours, they were able to ship the sample to IPD, and we confirmed that case. A month after, they detected the second yellow fever case during 2024, and also we were able to confirm that case. Last week, they shipped another sample from the dengue, which is the first time also in the history of the Gambia to detect an outbreak of dengue. So last week, we received that sample and we also confirmed the same pathogen. So that means we should be very proud as IPD, because 2 years ago, the Gambia does not have the capacity, not even to detect, but also to be able to confirm at the national public health level. Today, look at what they have been doing so far. So now, when the Cabo Verde, during the implementation of the setting up phase, there was an ongoing dengue outbreak. So it's when we were training the staff, we detected an ongoing dengue outbreak. And we shipped, I even myself came with the sample to Dakar to be retested and confirmed. And they stay with that outbreak for a year. 2 months ago, I received the weekly updates when this outbreak was still going on, and they confirmed more than 8,000 dengue cases based on the strategy put in place in the Gambia. 3 weeks ago, I was with my team in Guinea-Conakry. We spent two weeks there. The one side was in the capital city, and the second one was in the forest region where Ebola, the West African Ebola started in the forest region of Guinea, which is called Gekedu. So we set up the second sentinel site there. Just last week, 2 weeks after putting the system in place, we received a call from the National Surveillance Director saying that the sentinel site will open in the capital city, just confirming in the first time in the history of Guinea a dengue outbreak. So that case was just confirmed last week. So this is just to show you that today we can say Africa started or begins to see the lights of hope, because some African countries today are able to detect their own outbreaks and to quickly respond after being trained by IPD. So, as I said, today Africa begins to see the light. It's because IPD is opening the eyes of Africa. Thank you very much.
Thank you, Dr. Diallo. Bamba, I think you're very tall also, so I'm going to give you the microphone back.
Right. So. Right. So, right. So, I'm very happy to be here today. Hi, everyone. First of all, allow me to congratulate the Pasteur Institute for this hard work that they have been doing since 100 years. And I will lay this upon the hand of the CEO, Dr. Amadou, and all the team. I'm very happy to be here today to talk about, we said solution, but I will also start by talking about some problems, and then see how we can fix it. It's all going to be about NCDs. I'm not sure we have discussed NCDs a lot during this conference, but the time has arrived. And how we can use integrative epidemiology, prevention, and maybe AI to tackle this huge wave of NCDs all across the globe, but particularly in Africa. As we can see, by 2050, almost all cases of death will be due to NCDs. This is clear now. What can we do? This is globally. In Africa, according to the WHO in 2022, there was 50 to 88% cause of death due to NCDs in 7 sub-Saharan African countries. And the economic loss due to NCDs is estimated to $84 trillion by 2030, according to Bloom. So it's high priority. Now let me focus on cardiovascular disease, which is what I know most. And over the 4 past decades, we know that primary prevention has helped to decrease 2/3 of CVD worldwide. But still, there is 1/3 remaining, and the most alarming thing is NCD is on raise, and we are expecting to have 24 million deaths due to NCDs by 2030. And when we talk about the risk factors, they are also on raise. Let's be fast. This is a couple of figures that I just plotted, and we show that in Africa, no matter where you are, east, west, north, south. I mean, overweight is raised, diabetes is raising, hypertension control, treated, diagnosis, undiagnosed, everything is raised. Luckily, we're smoking less and less, but it's not enough. Right. And so what is the solution? Primordial prevention. I mean, primordial prevention has been defined by Professor Stasser, an English professor in 1978, but hasn't been really used. And it is defined, it's before primary prevention and defined as preventing the development of risk factor before it happens. In 2010, the American Heart Association has re-emphasized this tool by developing the ideal cardiovascular health tool, which is a very simplified tool, with two components, biological component and behavioral component. And let's go fast. For each matrix, one can be categorized as being poor, ideal, or intermediate. And when we combine the 7 matrix also, we can be categorized as having a poor cardiovascular health, an intermediate cardiovascular health, or an ideal cardiovascular health. This tool has been used, like I cited, for at least 5,000 times. And as you can see here, a study using the ARI cohort, which is one of the big US cohort, have shown that compared to people with 0 matrix at the ideal level, those with 4 or more at the ideal level had a 5-fold decrease of incidence of cardiovascular disease, which is huge. This other study I published in 2020 in JAHA even showed that when we change our CV age in the life, middle age, we will decrease our risk of CVD and mortality. And as you can see here, there is even a 300% decrease, which is major. And then we even went far. We tried to assess in the elderly population, where we know that there is a coexisting morbidity and medication and so many things, like after 70 years old. Primordial prevention, can it still work? And the result was funny. It's never too late. It also works. This is a paper we published in JAC in 2017. With that being said, what is the status of primordial prevention in Africa? I mean, over there, among the 5,000 papers that cited the original research, I think there is not a paper from Africa, which is really, really bad. And because in Africa, on top of this, we know that, there is an epidemiological transition where now non-communicable diseases, communicable diseases, TB, malaria, HIV, are still here. We need to take into account the disease, but now our concern are NCDs, cardiovascular disease, cancer, diabetes, and so on. This is a paper we published with SOS Médecins, Dr. Massamba Diop, in 2019, showing that in Africa, in Senegal particularly, NCDs are going up and infectious diseases are going down, and they crossed in 2010. Another challenge, the lack of funding for NCDs. Please just follow the red. The burden of disease, NCDs, is more than 80%. Please keep following the red. For the funding, it received only 2%. I think I don't need to comment this figure. Another issue, in Africa, problem. The funding is weak, almost exclusively from Western countries, developing countries, and we know, as you can see, it's like a US or whatever. And then when they fund, they select the topic on which we should work on, and it's not always easy to tackle this. So, what is the I'm sure I'm really happy to see that. Leading institutes like Institut Pasteur are now investing on NCDs. I have been discussing this with several people from OPD, and congratulations for that. I think we need to push. And implementing primordial prevention in Africa is now I'm talking about the solutions. I start the solutions. Right, and again, this is it's funny because we, as member of the American Heart Association and the publication committee, we were working on a statement for primordial prevention in Africa. After 6 months, we just realized Calvin Labat, who is one of the leader of one of the daddy of preventive cardiology, he just told me, hey, I mean, what can be said that is new and exciting for readers, avoiding repetition and the family exhortation to do more and better with very limited resources in infrastructure, like everything. He said, no, let's just shift this and let's do it another way. Let's do things that are more suitable to Africa. And we've been working on that since since a year and a half, and it led to a publication. I mean, it was published last week, led by Dr. Majikenka, a brilliant cardiologist from Farm Hospital, Principal Hospital. And in this publication, we discuss like the strategy that can be effective to reduce in cities in Africa, how we can implement primordial prevention, and taking into account the socio-cultural, economic, and environmental context in Africa. Another ongoing step is like we are looking data for incidents in Africa, and this is one of our consortium. The Asande is a Zulu name that means grow and progress. And what we are doing is now we are gathering the existing data on NCD in Africa. It's not always reliable. We don't have time to go deep. We know what the global burden of disease means when it can go Africa. Like 95% of the data are just imputed. I mean, they're just making the data. I mean, for instance, in Senegal, if you don't have data in hypertension, they go to Kenya, they get some data in hypertension, they come to Senegal, they take some data on children, and then they do some modeling, and then they give you the hypertension data. Serious. And then what we do is also now to develop reliable data. Carol was talking about the life course approach, which is what we should do from birth to the end of life. I mean, that's how we should do epidemiology. And the aim is to build this reliable African data set. I'm not going to go deep in this consortium, but what we need to know is like we have 10 prospective cohorts and 60 cross-sectional cohorts. I mean, adding up to more than 500,000 individuals. And the idea is to create an open source data that can be used by everyone, like let's just say accessible upon reasonable requests, and we never know what's reasonable, but the data will be available to provide more and more information. Then now I will really talk about how AI can help. I mean, in our global health setting. Yes, I mean, there's nothing new about using AI in infectious diseases. I mean, I think I'm very pleased to say that. I'm always laughing. And, but I mean, yeah, I think there is we are reaching a level where AI can be very useful in Africa for diagnosis. I mean, I have heard, showing how we can implement AI on several tools, then we can be more efficient. Because yes, I mean, to the issue in most African countries, we have like 1 MD for 20K inhabitant, which is far from the 1 for 4,000 individual that is recommended by the WHO. And adding to this issue, we have this current trend, so we need to do something. AI is available, but we should also be careful with this slow bias. As you can see here, this shows the use of existing data. And I mean, we've got Africa, we can barely see it. It's like everything is coming from a very big US part. Another thing, this is how we use existing data. Now, where the data are coming from? It's a question. Guess where the data are not coming from, actually? Africa. I mean, so this is something also that we need to be careful. I mean, what are the solutions? I mean, of course, collaboration. I mean,
We need to enrich like the global public health data set. We need to empower research teams. And of course, capacity building. That's what the Pasteur Institute is doing. And of course, we need to increase representation in the data. That's what we're doing in the context of Data Science Africa. We don't have time to go deeper on this, but if there's any question after, we can discuss that. And yes, it is known that the next revolution on AI will likely be in the health sector. And we really believe that the Global South has the opportunity to be a leader. But it will ask to create data, to have representativeness, and of course, I mean, we hear a lot about the Silicon Valley, but maybe it's time to hear also a lot about the Silicon Savannah and all the African hubs and technology to lead the AI, because there is existing things in sub-Saharan Africa. We should not deny that. Last but not least, how we can do this? I mean, in the context of our alliance, the Alliance for Medical Research in Africa, which is in 33 countries, that's what we're doing. We develop talent, we foster collaboration, we also translate research into policy. And this is Data Science Africa. I was very proud to see all those data scientists, engineers, mathematicians, MDs gathered those in Kenya nearly a couple of months ago. And I mean, delivering high-level science. So we have capacity here. We can move forward. That's what Dr. Jallo was saying. And also the South-South collaboration. And we strongly believe in telehealth, how we can empower the local physician and to deliver more, because in some part of the country, we may not have sufficient MDs to perform what is required. So telehealth is definitely something that can help. And so an example, this Capgemini AI study is we're using those large language model to develop a comprehensive approach to revolutionary ECG diagnosis in training in Senegal. We're happy to discuss more this study. We have also, I mean, this is one of the studies, really, when I was a postdoc in Karolinska Institute like 7 years ago. And we aim to develop the first machine learning model that can help to identify the bicuspid outer valve with high probability of doing aneurysm. Because, I mean, I'm going to go deep in physiopathology, but we failed to develop this tool. But yet, I mean, now what we say is, okay, we are in Karolinska, they have huge data, but yet we failed. Now we will do it in Africa. The answer we will come from Africa, and with our Karolinska team, Professor Pierre Erickson was a mentor during my postdoc, and now half retired. We will be employed as part of a team, and we are now developing this epidemiology of congenital bicuspid valve in Africa, led also by Dr. Rone and Dr. Majidi. And I will finish with this. I mean, science is also meant for advocacy, and I'm glad to see that things are moving in Africa. This is an example, just one quick two slides reminding me when the COVID outbreak came. I mean, at the time I was still Samy de Paris. I mean, where definitely the Samy is weighing forward, and it had 2 minutes about like what to die. I mean, it's like a very serious. And each day we receive 2,000 calls. And that Friday where everything went wild, went from 2,000 calls to 12,000 calls. And to be honest, even the cleaning guy was good to come and help. But yet, I felt like the major issue of I mean, I'm going to say foreign, but Western countries was how things will go in Africa. And then seeing so many
idea from here and there, predicting that everyone is going to die in Africa, is going to burn, whatever. You don't give any evidence. You just perpetrated stereotype. I mean, how can this be possible? And what we did is like we did this study in which we definitely estimated the how the pandemic will happen in Africa, and show that everything is going to be all right. At the time, we were calling us Afro-centrists or whatever, but yet we were even blackmailed. But at the end of the day, what we predicted is what happened, and everything went well. So, to sum up, I really believe that to achieve our goal, we should make sure to train NCDs people, all over the country, and stop to because several specialists in cardiologists, nephrologists, and we should work together. Which is the point number 2: collaboration within NCD specialists. And of course, we should never deny the existence of infectious disease, which is here and prevalent. So we should work together, take into account the interplay between NCD and infectious disease. And also, as I saw, there's a lot of surveillance data, and we should do more for NCDs and provide also training in epidemiology, methodology, and statistics. That's what we are doing in our network. This will allow to ensure that we have enough good quality data. Then, when we have this good quality data, we can use deep methodology to better understand African NCDs, because NCDs in Africa cannot be similar to NCDs elsewhere, and we have already determinant. And then what is critical is to enable young African researchers to create and conduct their research that are defined by themselves, to study the test of their choice, and then to analyze the study themselves, to publish it themselves, and actually benefit from the result. Because we know publication is, we pay when you publish, but publication is money. It helps you to have more visibility. When you apply for a grant, I think the publication will always help. So that's what I see as a solution. Thank you.
Okay, just to go through a quick round of questions for all the panelists, and then we can open it up to the floor for some additional questions. So I'll start with Bamba. You made me feel guilty as a person that focuses on infectious diseases, which I'm sure, yes. So the subject of the panel this afternoon is about resilience. And so maybe if you could just spend a minute or two of the research that you expressed, not just focusing on NCDs, but maybe the rest. How does what you do improve resilience in health systems?
Very good question. Thank you. First of all, let me say that I'm not an expert in health systems. I think being said, resilience, it's something that we will need to redefine, but I will answer the question, how we use resilience to do what we're doing. This is something I can try to answer. And to be honest, we have been developing so many things on NCDs without any funding. I think this is the definition of resilience. I really believe that we can do so many things without funding, and there is no choice anymore. It's possible to do small things. And try to answer or to tackle the ongoing issues. That's the only thing I will answer. Thank you.
I think you're very right. We can do lots of things without money. Dr. Diallo, maybe quickly about the 4S system and the success that you've had in terms of rolling this out across West Africa. Could you discuss a little bit what is the biggest resistance? Is it authorities in other countries? Is it other practitioners? Who are the hardest people to convince to roll out the system?
Basically, for now, we have not seen any resistance from the country yet. As because before going to countries, we contacted the Minister of Health first to share the idea and also the concept notes. As soon as it's approved, so we will come first to do the first visits and to do the assessment. And then after that, we invite the hosting country to come to Senegal to visit some of our syndromic sentinel sites. So to inspire them. And then after that, we go work with the Minister of Health staff and going to those sentinel sites. The main problem could be, there is no motivations around the system because it's not a parallel system. It's an integrated surveillance system that will go through the national surveillance system. Sometimes, healthcare workers may say, what kind of motivation do we get from that new system that is being put in place? But, if everything is not like money, but what we usually do, for example, in Senegal, so because of the FLTP training, some of our syndromic sentinel sites that are at the primary healthcare level, where we have some nurses that are doing a great job because without having any skills. So now we are pushing the MOH when there is a FLTP training so that we can include them into that training to really strengthen their capacity.
Yeah, thank you very much. I think just to point out also what you said right at the beginning is a good example of what was mentioned in the video in terms of how to prevent potentially future disasters, and it was applied to the forest system.
Exactly.
We'll go quickly to Carell. I know you, so I'll ask you a tougher question. More so. So I thought it was interesting on your slide, and I just wanted to hear your comments about your presentation, which is to be lauded for IPD to be doing this work at the same time. It's looking at the entire value chain. But you didn't have people and communities listed in the definition of health systems. And I was curious as to whether that was the WHO definition, which didn't include that.
So that's true, actually. So the WHO definition, as I quoted it, that's the official definition. But it's true that in the framework, people are at the center. They are there. I probably should have clarified that. But the whole approach of health systems is focused on people and on communities. So just to clarify that for you, Rebecca.
Thank you, Carell. Heidi, maybe just one final question to wrap up this session for you to answer as you started is the video that you showed and the work that you do applies to vaccines, but it applies to much more than that. And it applies principally, I would think, to trust in different people. So when you think about the work that was just presented, if there's areas that you want to discuss which you feel which are both positive and others where those might be other future areas for IPD to invest in terms of the community, that would be great.
Oops. While the Ghana film and the work that we did collaboratively with Carell on the vaccine confidence is on vaccines. The first slide I showed was from a much bigger study we're doing that is well beyond vaccines, and it was on societal response and experience of the collective of COVID measures, and basically to see who do people trust, who do they turn to. So those lists, those countries that were listed, those questions were in the context of the broader, in a crisis when you're asked to do a million things beyond jabs and arms. Who do you trust? Who do you turn to? But does that help?
Yeah, it was just both to congratulate IPD in the work that we just heard for Senegal, and also if you had other areas where you think that the methodology that you've been using would be applied.
Yeah, well, I think CARE. I'm on the scientific advisory board with CARE and the Center for Pandemic or Response Measures, Crisis Response. I think it's a crucial. I mean, it's a fantastic initiative. I think some of the work we're doing can bring the societal preparedness into it. I think it's relevant to any. I mean, when you talk about NCDs, most of the prevention is at a people level, at a community level, and so it's. I mean, I was thinking it's a great one to land on because NCDs are about as the most health behavior relevant area of health. So behavioral stuff matters more than anything.
That's great. I think we'll have to wrap up this session because we're a little bit far behind. And I'll just end on two notes. The first one is Heidi was referring to the Center for African Resilience to Epidemics, which is based here at IPD. For those of you that don't know what that is, you should. And it can certainly be a center point for the region and beyond the region in terms of addressing both science, resilience, and public health. And then the last thing is something that Bamba mentioned, and that's just for the scientists in the room, is, publications sort of only go so far. We talk a lot about the need to have scientifically literate politicians, but we also need policy literate scientists. And I think the discussion today is a first step in that direction. And so I do hope that that's something that CARE does. And the work that's done at IPD is also a great example of that. So, Aisha.
So yes, thank you to all our panelists and Rebecca for moderating. Please give a huge round of applause for all of them. You can all leave the stage. So, dear guest, we've come to the end of the day. But before that, actually, the panelists, did you mind taking a picture together? Sorry. Okay, so like I was saying, we've come to the end of the day, and we've also come to the end of this Centenary Celebrations 2-day scientific symposium. It has been an honor to be your MC and to witness the great achievements and successes that we have celebrated today. Throughout the symposium, we have honored those who have made outstanding contributions to their fields, as well as those who have demonstrated exceptional leadership and service. We have also recognized the hard work and dedication of everyone across the research and global health spectrum, from our students, researchers, all the practitioners at the IPD and partner institutions, and the important role that each have played in the success of the IPD and also the success of global health. To all of you, our esteemed speakers and audience, thank you for your active participation and for making this ceremony a resounding success. Your presence and engagement have been instrumental in creating a very vibrant and celebratory atmosphere. As we close this ceremony, I would want to remind everyone of the importance of perseverance, hard work, and the power of dreams, like Dr. Marco said. These are the qualities that have kept the IPD as a leading force in research and now also in innovation 100 years after, and has brought each of us to where we are now. At this juncture, I would also like you to join me in recognizing and applauding the organizing teams of the symposium, led by Dr. Amadou Sall and Dr. Xavier Berdet, the IPD Centenary team, and all our partners who have contributed in making this event possible. I would like to thank you all once again for joining. But as I leave the stage, I would like to welcome Dr. Xavier Berdet, who will close this symposium. So a huge round of applause for everyone and for him.
Hello, everyone. You know, I was born in the Alps, in a place where the valleys are very deep and the connections very remote. So we are people of very few words, and we have a saying that among the people who have nothing to say, the ones who shut up are the best. So I will try to be very short. I hope you enjoyed the centenary. You will probably not see the next one. So we hope it has been a very brilliant and thrilling moment. We have been extraordinarily proud to put ahead our projects, our discoveries, but overall our people. And we are very happy that most of you have started to weave some collaborations with these new, young, and brilliant scientists. And we hope that the next century will be paved by these interactions. So thank you very much for being with us, and let's have a very fruitful week. Thank you very much.
Sorry, I thought I was done. The ceremony is now officially closed. You can all go back to the room where we have a cocktail to end the day.